Hello, sleepy soul. Welcome back to Slow Science, your sanctuary for the unhurried mind. If you're hearing this now, in the quiet hours, let yourself settle. Let your shoulders drop. Let the weight of the day dissolve into the darkness around you. There's nowhere you need to be, nothing you need to remember, nothing you need to solve. Tonight, we're drifting together into the slow, patient glow of red giants, those ancient, swollen stars that burn softly in the cosmic night. These are stars in their twilight, vast, luminous, and impossibly gentle. They've been shining for billions of years, and they'll continue long after you've found your rest. You don't need to follow every word. You don't need to remember the details. Let the facts wash over you like waves on a distant shore. If you drift away, that's exactly what should happen. If you wake in the middle and hear my voice still here, know that you're safe, that the universe is vast and patient, and that sleep will find you again. So close your eyes if you haven't already. Let your breathing slow. Feel yourself sinking into the quiet wonder of stellar time, where everything moves at the pace of ages and nothing demands your attention. Let's begin. Imagine for a moment a star, not the sharp, white points of light you see on a clear winter night, but something older, something softer. A star that has lived for 5 billion years, 10 billion years, burning steadily in the black, watching galaxies turn, watching planets form and cool, and perhaps even cradle life. And now, in its old age, the star is changing. Its core is cooling, its fuel running low, and in response, the star is doing something beautiful. It is swelling, growing, expanding outward like a slow, luminous breath. Its outer layers drift into space, glowing red and orange, casting a gentle warmth across the void. These are the red giants. They are not violent. They are not sudden. They are the embodiment of cosmic patience. Stars in the midst of a transformation that will take millions of years. And tonight, we will explore them together, fact by gentle fact, letting their ancient light carry us into sleep. There is no rush. There is no climax to the story. Just a slow expansion of starlight, the quiet hum of nuclear fusion in distant shells of hydrogen, and the deep, deep time of the universe unfolding around us. So settle in, let the darkness hold you, and let's drift into the red glow of these magnificent, aging stars. Red giants represent a dramatic late stage in stellar evolution for stars like our sun. But let's pause there for a moment, because the word dramatic in the cosmic sense is not the same as our human sense of drama. There are no explosions here, no sudden changes. The drama of a red giant is the drama of a glacier carving a valley, slow, inevitable, and impossibly vast in scale. Every star that shines in the night sky is on a journey, a long, slow journey from birth to transformation. Stars are not eternal, though they live so long that to us, they might as well be. They are born in clouds of gas and dust, collapsing under their own gravity until their cores grow so hot, so dense, that hydrogen atoms begin to fuse into helium. and then they shine. For billions of years, they shine. Our sun has been shining for about 4.5 billion years. It will continue to shine, much as it does now, for another 5 billion years. And then, slowly, over the course of millions of years, it will begin to change. It will swell. It will cool on the surface. Even as its core grows hotter, it will become a red giant. This is not a disaster. This is not an ending. It is simply the next chapter in the life of a star. A chapter written in light and heat and the patient, inexorable laws of physics. When we look up at the night sky and see a red star glowing softly among the white and blue points of light, we are seeing a star in its old age. We are seeing a sun that has burned for billions of years, transformed, swollen to an enormous size, and now drifts through space like a vast, glowing ember. There is something deeply calming about this. These stars have existed for longer than our planet, longer than our species, longer than the continents or the oceans or the mountains. They have seen the universe change around them, and still they burn, slowly, gently, with no hurry at all. And tonight, as you listen, you are connected to that deep time. You are drifting in the same universe as these ancient stars, and you are allowed to rest. You are allowed to let go of the need to hurry, to solve, to remember. Just like a red giant, you can simply be existing in the quiet glow of the present moment. Breathe slowly. Let the image of a red star fill your mind, vast, soft, glowing warmly in the endless dark. And let that warmth carry you deeper into rest. Stars become red giants after exhausting hydrogen in their cores after billions of years on the main sequence. The main sequence. It's a term astronomers use to describe the long, stable phase of a star's life. It's where most stars spend most of their time. It's where our sun is right now, fusing hydrogen into helium in its core, radiating light and heat, holding itself up against the crushing weight of its own gravity. For a star like the sun, this phase lasts about 10 billion years. 10 billion years of steady burning. 10 billion years of hydrogen atoms colliding in the fierce, million-degree heat of the core, fusing together, releasing energy, keeping the star shining. But even the largest fuel supply eventually runs low. After billions of years, the hydrogen in the very center of the star is gone, used up, fused into helium, and the core, now made of helium, can no longer generate the heat and pressure needed to hold itself up, so it begins to contract, slowly, gently, pulled inward by gravity. And this is where the transformation begins. There is something almost melancholy about this moment. If we think of stars as living things, the core, once bright and hot and full of fuel, now grows quiet. It shrinks. It cools at first, but the star is not done. Not yet, because as the core contracts, the layers just outside the core grow hotter. The hydrogen that still remains in the shell around the helium core begins to burn. And this hydrogen shell burning is what drives the next phase of the star's life. The star begins to swell, its outer layers expand outward, driven by the energy of this new shell of fusion. The surface cools, shifting from white or yellow to orange and red. The star grows larger and larger until it is enormous, hundreds of times its original size, and it becomes a red giant. This process is slow. It takes millions of years for the transformation to complete. If you could watch a star become a red giant, you would see nothing change from night to night, or even from year to year. Only over the course of millennia would you notice the star growing brighter, redder, larger in the sky. But eventually you would see it, a vast, glowing sphere, dwarfing the star it once was, burning softly in the darkness. There is no violence here, no sudden shift, just a patient unfolding of stellar physics, playing out over timescales so vast that our entire history, all of human civilization, is a single, brief flicker in comparison. And in that vastness, there is peace. There is permission to let go of the rush, the urgency, the need to force things to happen quickly. The universe operates on its own timeline, and it does not hurry. Neither do you need to hurry now. Let your breathing slow. Let your thoughts drift. Let the image of a star, slowly swelling into a red giant over the course of eons, remind you that change is slow and that rest is natural. You are safe in this moment. You are held by the same gravity that holds the stars, and sleep is waiting for you just beyond the edge of thought. This process takes about 5 to 10 billion years for sun-like stars. 5 billion years. Let that number settle for a moment. 5 billion years. It's a span of time so long that it almost loses meaning. Our planet Earth is only about 4.5 billion years old. The oldest known rocks on Earth's surface are just over 4 billion years old. The first life, simple, single-celled organisms appeared perhaps 3.5 billion years ago. 5 billion years ago, the sun was just beginning its life. The solar system was forming. There was no Earth yet, not as we know it. Just clouds of dust and gas, slowly collapsing, slowly coalescing into planets. And the sun began to burn. 4 or 5 billion years, it has been fusing hydrogen into helium. 4 or 5 billion years, it has been shining, steady and bright, warming the planets that orbit it, and it will continue to do so for another 5 billion years, until eventually the hydrogen in its core runs out and the transformation begins. 5 to 10 billion years. That is how long it takes for a star like the sun to reach the red giant phase. There is something profoundly restful about contemplating this kind of time. It is so far beyond our human experience that it ceases to be stressful. We cannot worry about 5 billion years. We cannot plan for it. We cannot control it. We can only acknowledge it, marvel at it, and let it remind us of how small and brief our own lives are in the cosmic scale, and that smallness is not a burden. It is a release. You do not need to carry the weight of eternity. You do not need to solve problems that will outlast you by billions of years. You are here now, in this moment, and that is enough. The stars will continue to burn, whether you are awake or asleep. The universe will continue to unfold, patient and vast, and you are allowed to rest within it. Imagine a star burning quietly for 5 billion years. Imagine the steady, relentless fusion at its core, atom by atom, moment by moment, for longer than continents have existed. And imagine that star now in its twilight, beginning the slow transformation into something new. There is no rush. There is no deadline. The star has all the time in the universe. And so do you in this moment. Let yourself drift. Let the numbers fade. Let the vastness of stellar time carry you into the quiet, warm darkness of sleep. On Hertzsprung Russell diagrams, red giants trace the red giant branch upward. Now we enter the realm of diagrams and graphs, tools that astronomers use to map the lives of stars. But don't let the technical language pull you back into wakefulness. Let it be like a lullaby, words that wash over you, patterns that you don't need to fully understand. The Hertzsprung Russell diagram is a map of stars. On one axis, it shows luminosity, how brightly a star shines. On the other axis, it shows temperature, how hot the star's surface is. And when you plot thousands of stars on this diagram, patterns emerge. Most stars cluster along a diagonal line, from hot and bright to cool and dim. This is the main sequence, where stars like our sun spend most of their lives. But above this line, in the upper right corner of the diagram, there is another branch, a cluster of stars that are bright, very bright, but cool, red. These are the red giants. And if you could watch a single star over billions of years and track its position on this diagram, you would see it move. Slowly, it would drift upward along the red giant branch, growing brighter and cooler, tracing an arc to the map of stellar life. This upward path is not random. It is determined by physics, by the structure of the star, the pressure in its core, the fusion reactions in the shell around the core. As the star ages, as it burns through its fuel, it climbs this branch, step by step, becoming more luminous, more swollen, more deeply red. There's a rhythm to this, a predictability. Stars of certain mass will always follow a certain path. They will always reach a certain brightness. They will always swell to a certain size. The universe is full of patterns, and this is one of them. A pattern written in light and gravity and time. And there is comfort in patterns. Comfort in knowing that the universe follows rules, that stars age in predictable ways, that the chaos we sometimes feel in our own lives is not reflected in the steady, patient burn of distant suns. Let the Hertzsprung Russell diagram fade from your mind. Let the image blur into abstraction. You don't need to remember the axes or the branches. You only need to know that stars follow a path, and that path is slow and luminous and inevitable. Just like sleep, it is coming for you, slowly, inevitably, and you don't need to force it. You only need to allow it. Breathe, let go, and drift upward like a star on a diagram, into the bright, soft glow of rest. Neon luminosity marks hydrogen exhaust, launching rapid ascent on HR diagram. There is a moment in the life of a star when something shifts. For billions of years, the star's been burning steadily, fusing hydrogen in its core, sitting comfortably on the main sequence. Its brightness has been relatively constant. Its size has changed very little. It is stable. But then, the hydrogen in the core runs out, and at that moment, that precise moment, the star's luminosity begins to change. On the Hertzsprung-Russell diagram, this moment shows up as a knee, a sharp bend in the star's evolutionary track. It is the point where the star stops moving horizontally and begins to move upward, climbing the red giant branch. Astronomers call this the knee because it looks like the joint in a leg where the path bends suddenly. But don't be fooled by the word rapid. In the cosmic sense, this rapid ascent still takes millions of years. The star brightens, slowly but steadily. Its core contracts, heating up. The shell of hydrogen around the core ignites, burning fiercely, and the energy from this shell burning drives the outer layers of the star outward. The star swells. It cools on the surface. It becomes redder, brighter, more luminous, and on the diagram it climbs up and to the right, tracing a path that billions of other stars have traced before it, and billions more will trace after. There is something almost graceful about this. The way a star responds to the exhaustion of its fuel is not to collapse entirely, not to fade away. Instead, it transforms. It finds a new source of energy, a new way to shine, and it becomes something even more magnificent than it was before. This is the knee, the turning point, the moment where old age becomes a new kind of beauty. And perhaps there is a lesson here, if you want to take it, or perhaps there is not. Perhaps it is enough to simply know that stars change, that they adapt, that they continue to glow even when their cores are gone quiet. Let the knee and luminosity be a turning point for you, too. A moment where you stop trying to hold on to the day and allow yourself to turn towards sleep, to climb upward, not in brightness, but in depth, into the warm, dark embrace of rest. You don't need to remember this fact. You don't need to visualize the diagram. Just let the words drift past you like clouds across a night sky, and let yourself turn gently, slowly towards sleep. Gravity then contracts the core, heating surrounding layers until they ignite. Gravity is patient. It is always there, always pulling, always drawing matter inward. In a star, gravity is a force that wants to collapse everything into a single, dense point. It is the weight of 1,000,000 Earths. Pressing down on the core, try to crush it. But for billions of years, the star resists. The fusion reactions in the core, the hydrogen atoms colliding and fusing into helium, release enough energy to push outward, to hold the star up, to keep it from collapsing. This is called hydrostatic equilibrium, a balance. Gravity pulls in, fusion pushes out, and the star remains stable. But when the hydrogen in the core runs out, that balance shifts. There is no more fusion in the core, No more outward pressure, and gravity, patient as ever, begins to win. The core contracts. It shrinks slowly, pulled inward by its own weight. And as it contracts, it heats up. This is a law of physics. When you compress a gas, it gets hotter. Squeeze a bicycle pump, and the air inside warms. Compress a stellar core by the weight of 1 billion atmospheres, and it grows searingly hot. And eventually, that heat spreads outward into the layers surrounding the core. These layers are still full of hydrogen. They haven't been fused yet. And when they reach a certain temperature, a certain threshold of heat and pressure, they ignite. Suddenly, there is a new source of fusion, not in the core, but in a shell around the core. A thin, glowing shell of hydrogen burning fiercely, releasing energy, pushing the outer layers of the star outward, and the star begins to swell. This is the mechanism. Gravity contracts the core. The core heats the surrounding layers. The surrounding layers ignite, and the star transforms. There is no resistance here, no struggle, just the inevitable interplay of forces, playing out over millions of years. Gravity does what gravity does. Heat does what heat does. And the star responds, adapting, changing, becoming something new. Let this image settle in your mind. The slow contraction of the core, the gradual heating, the moment of ignition, like a candle being lit in the darkness, and then the swelling, the expansion, the transformation into a red giant. It is a slow process, a gentle process, and it requires no effort from you to understand or remember. Just let it wash over you. Let the warmth of that igniting shell spread through your awareness, and let it carry you deeper into the warmth of sleep. Gravity pulls, heat rises, and you are allowed to let go, to sink, to rest. Hydrogen shell burning outside the core causes ongoing expansion. Once the hydrogen shell ignites, the star's fate is sealed, not in a tragic sense, not in a catastrophic sense, but in the sense that the star is now on a path. It will follow that path for millions of years, driven by the fusion reactions in the shell around its core. Hydrogen shell burning. It's a technical term, but let it roll over you like a wave. You don't need to grasp every detail. Just know that there's a layer of the star, a thin shell, where hydrogen is fusing into helium. And this fusion releases enormous amounts of energy. More energy, in fact, than the star was producing when it was on the main sequence. This might seem paradoxical. The star has run out of fuel in its core. So shouldn't it be dimming, fading away? But no, the shell burning is so efficient, so intense, that the star actually becomes brighter, more luminous. It shines with a light it never had in its youth. And all that energy has to go somewhere. It pushes outward against the outer layers of the star. It drives them away from the core, expanding the star to enormous sizes. The surface of the star moves farther and farther from the center, cooling as it goes, shifting from yellow to orange to deep, glowing red. The star swells, slowly, steadily. And as long as there is hydrogen in the shell to burn, the expansion continues. This is not a violent explosion. There are no shock waves, no sudden bursts. Just a slow, relentless push, like a flower opening in time-lapse, spreading its petals over the course of ages. And there is something deeply soothing about this image. The idea that growth can be slow, that transformation doesn't have to be sudden or painful, that a star can expand hundreds of times its original size over millions of years, and that this is simply the natural course of things. You, too, are allowed to expand, to grow, to change at your own pace. There is no rush. There is no deadline. The universe does not hurry, and neither should you. Let the hydrogen shell burn in your imagination. Let the star swell gently, slowly, filling the darkness with its soft, red glow. And let that glow fill your mind, pushing away thoughts, pushing away worries, leaving only warmth and space and a gentle drift towards sleep. This mirror principle links core contraction to envelope swelling. There's a beautiful symmetry in the heart of a red giant. As the core contracts, the envelope expands. As the center grows smaller and denser and hotter, the outer layers grow larger and more diffuse and cooler. This is the mirror principle, a term that captures the elegant balance at work in an aging star. It is as if the star is pulling inward at its heart, and that inward pull is reflected outward in the swelling of its surface. Imagine a balloon. If you squeeze the middle, the ends bulge out. The total amount of material hasn't changed, but the shape has. The star is similar, though infinitely more complex. The core compresses under its own gravity, and the energy from the shell burning drives the envelope outward. Contraction mirrors expansion. Heating mirrors cooling. Density mirrors diffusion. And this balance is not chaotic. It is not random. It is governed by the laws of thermodynamics, by the structure of the star, by the precise interplay of pressure and temperature and gravity. There is order here. There is pattern. And in that pattern, there is peace. The universe is full of these kinds of symmetries, these mirror relationships. Day mirrors night. Summer mirrors winter. Inhalation mirrors exhalation. And in a red giant, the contraction of the core mirrors the swelling of the envelope. Let this symmetry calm you. Let it remind you that the universe is balanced, that for every inward pull there's an outward push, that nothing is truly lost or gained, only transformed. And let yourself mirror the star as you contract your awareness, pulling it inward, away from the world, away from thoughts. Let your sense of peace expand. Let calmness swell outward, filling your body, filling your mind, until there is nothing left but the quiet, warm glow of rest. The core contracts, the envelope swells, and you are allowed to simply be balanced between waking and sleep, drifting gently into the darkness. The star's outer layers expand massively, up to 100 to 250 times their original size. 100 times. 200 times. 250 times. Imagine the sun, imagine its surface, that glowing yellow sphere, 1.4 million kilometers across. Imagine the Earth, a tiny blue marble orbiting 150 million kilometers away. Now imagine the sun swelling, growing larger, larger still, its surface expanding outward, past the orbit of Mercury, past the orbit of Venus, reaching toward the Earth itself. This is what will happen billions of years from now when the sun becomes a red giant. Its outer layers will expand to 100 times their current size, perhaps more. The surface of the sun will extend past the orbit of our planet, swallowing Mercury and Venus, and possibly even Earth. But this will not happen tomorrow, or next year, or in 1,000,000 years. It will happen in 5 billion years, give or take, and it will take millions of years to complete. So there is no urgency, no threat, only the slow, inevitable unfolding of stellar physics. For now, the sun is stable. For now, the Earth is safe. For now, we can look up at the night sky and see other stars that have already made this transformation. Stars that have swollen to enormous sizes, glowing red and soft in the darkness. Betelgeuse, Aldebaran, Arcturus. These are red giants, each one hundreds of times larger than the sun. If you place them where the sun is, their surfaces will extend past the asteroid belt. They are vast beyond comprehension, and yet they are gentle. Their surfaces are cool. Their light is soft. They do not blaze like young, hot stars. They glow like embers. Let this vastness wash over you. Let the image of a star, swollen to 200 times its original size, fill your mind, and let it remind you of how small you are, how brief your worries are, how insignificant the stresses of the day become when set against the scale of the cosmos. You are a tiny point of awareness in an unimaginably vast universe, and that is not a burden. It is a gift. It means you can let go. You can stop trying to hold everything together. You can trust that the universe will continue, whether you are awake or asleep. The star swells, slowly, gently, and you can swell into sleep the same way, expanding outward, letting go of boundaries, dissolving into the warm, soft darkness. Radii reach 200 to 1,000 times the sun's. Those size alone doesn't define supergiant status. 200 times the sun, 500 times, 1,000 times. These numbers are almost impossible to grasp. If you were to fly a spaceship from one side of a supergiant star to the other, traveling at the speed of light, the fastest speed possible in the universe, it would take you hours to cross a single star. The sun, by comparison, takes only a few seconds to cross at the speed of light. It is large, yes, by human standards, but compared to a red supergiant, it is tiny. And yet, size alone does not make a star a supergiant. Supergiant is a classification based on luminosity, not just size. A supergiant is extraordinarily bright, shining with the light of thousands or even hundreds of thousands of suns. Red giants, by contrast, are bright, but not that bright. They are large, but not always the largest. The distinction is subtle, technical, and you don't need to remember it. Let it drift past you like a piece of trivia, interesting for a moment, then gone. What matters is the image, the vast, glowing sphere of a red giant, hanging in space, dwarfing planets, dwarfing even the star it once was. A star in its old age, transformed by time and physics into something beautiful and strange. These stars are not rare. The night sky is full of them. Every red point of light you see might be a red giant burning softly billions of miles away. They are part of the cosmic landscape, part of the cycle of stellar life and death and rebirth. And they are patient. They burn slowly. They expand slowly. They have existed for billions of years, and they will continue for millions more. Let their patience become your patience. Let their slow, steady glow remind you that there is no hurry, no rush, no need to force anything. Sleep will come when it comes. Rest will find you when you allow it. The star reaches 200 times, 500 times, 1,000 times the sun's radius. And you are allowed to simply exist, vast and quiet in this moment. Let the numbers fade. Let the sizes blur into abstraction. And let yourself drift gently into the infinite, patient darkness of sleep. Cooler surface temperatures, around 3,000 to 5,000 Kelvin, give the star its red hue, 3,000 Kelvin. To put that in perspective, the surface of the sun, the bright yellow sphere we see during the day, is about 5,800 Kelvin. That's hot enough to vaporize any known material instantly. Hot enough that if you could somehow stand on the surface, you would cease to exist in less than a millisecond. But a red giant is cooler, not cool in any human sense. 3,000 Kelvin is still over 2,700 degrees Celsius. Still hot enough to melt tungsten, to boil steel, to turn rock into glowing vapor. But compared to the sun, compared to other stars, it is cool. And that coolness changes everything. When an object is heated, it glows. A piece of metal in a forge starts to glow red, then orange, then yellow, then white as it gets hotter. This is called blackbody radiation, and it follows a simple rule. The hotter the object, the bluer the light it emits. The cooler the object, the redder. A young, hot star glows blue or white. Its surface is 10,000 Kelvin, 20,000 Kelvin, even 40,000 Kelvin for the hottest stars. These are the bright, fierce stars, the ones that burn fast and die young. But a red giant is cooled. Its surface has drifted down to 3,000 or 4,000 or 5,000 Kelvin. And at that temperature, the light it emits is predominantly red and orange, warm colors, soft colors, the colors of embers in sunset and firelight. This is why we call them red giants. Not because they are angry or violent, but because they glow with the gentle, deep hue of a cooling flame. And there is something inherently calming about red light. Studies have shown that red light, does not disrupt melatonin production the way blue light does. It does not trigger the same alertness response in the brain. It is the color of dusk, of candles, of the fading day. It is the color that tells your body it is time to rest. So when you imagine a red giant, imagine that soft, warm glow. Imagine a star the size of Earth's orbit, glowing like a vast ember in the darkness. Not harsh, not blinding, just warm, gentle, a presence in the night that asks nothing of you, that simply exists, radiating its quiet light into the void. Let that red light fill your mind. Let it wash over you like a warm blanket. Let it remind you that even the stars in their old age grow cooler, softer, more gentle. And let yourself cool, too. Let the heat of the day drain away. Let your thoughts slow, your breathing deepen, your body settle into the mattress beneath you. The star glows red, 3,000 Kelvin, and you are allowed to simply rest in that glow, warm and safe and drifting towards sleep. Opacity effects from titanium oxide and vanadium oxide bands trap heat, puffing envelopes despite cooling surfaces. Now we enter the realm of molecular physics. But don't tense up. Don't try to understand every word. Let the language wash over you like the sound of rain on a window. Present, but not demanding. Opacity. It's a measure of how well a material blocks light. A clear window has low opacity. A brick wall has high opacity. And in the atmosphere of a red giant, certain molecules, titanium oxide, vanadium oxide, create regions of very high opacity. These molecules form in the cooler outer layers of the star, and they have a peculiar property. They absorb light very efficiently at certain wavelengths. They trap photons, preventing them from escaping into space. And when light is trapped, it deposits its energy as heat. So even though the surface of the red giant is cooling, even though it's radiating red light into space, the layers just beneath the surface are being heated by this trapped radiation. The titanium oxide and vanadium oxide act like a greenhouse, holding heat in, preventing it from escaping. And that heat creates pressure, outward pressure, pushing the envelope of the star outward, puffing it up like a balloon being slowly inflated. This is why red giants can grow so large. It's not just the fusion reactions in the shell around the core. It's also these opacity effects, these molecular bands that trap heat and drive the expansion. There is something almost paradoxical about this. The star is cooling on the outside, and yet it is swelling. It is losing energy to space, and yet it is growing larger. But the paradox resolves when you understand the layers, the depth, the complex interplay of radiation and matter. You don't need to remember the names of the molecules. Titanium oxide, vanadium oxide. Let them be sounds, not concepts. Let them drift past you like the names of distant cities you will never visit. What matters is the image, the star, cooling on the surface, glowing red. And beneath that surface, heat trapped by invisible molecules, pushing outward, swelling the star to enormous sizes. It is a slow process, a gentle process. The opacity increases gradually as the star cools. The envelope expands over millions of years. There is no sudden moment where the star puffs up, just a slow, steady growth, driven by the quiet physics of light and matter. And in that slowness, there is peace. The universe does not rush. The stars do not hurry. And you are part of the same universe, governed by the same laws of patience and time. Let the opacity trap your thoughts. Let them be absorbed, held, unable to escape. Let the pressure of wakefulness dissipate, and let yourself expand into the soft, warm darkness of sleep. The star puffs outward, slowly, gently, and so can you. Stars grow brighter, up to thousands of times the sun's luminosity. This is where the red giant defies our intuition. The star has run out of fuel in its core. It is cooling on the surface. It is in its old age, approaching the end of its life. Surely, we might think it should be dimming, fading away like a dying ember. But no, the red giant grows brighter, much brighter. Some red giants shine hundreds of times more brightly than the sun. Others, the largest and most luminous, shine thousands of times brighter. If you could replace the sun with a red giant, the earth would be bathed in light so intense that the oceans would boil away. The atmosphere would be stripped off. The surface would be scorched to molten rock. But how? How can a cooling star grow brighter? The answer lies in size. Luminosity, the total amount of light a star emits, depends on two things: temperature and size. A hot star is more luminous than a cool star the same size. But a large star can be more luminous than a small star, even if it's cooler. And red giants are large, enormously large. The surface of a red giant might be cooler than the sun's surface, but that surface is spread over an area hundreds or thousands of times larger. And when you add up all the light coming from that vast surface, the total luminosity can dwarf the sun's output. Imagine a single candle. It gives off a certain amount of light. Now imagine 1,000,000 candles spread out over a football field. Each candle is the same brightness as the first, but together they illuminate the entire field, far more brightly than a single candle ever could. The red giant is like those 1,000,000 candles. Each square meter of its surface is dimmer than the sun's. But there are so many square meters, so much surface area, that the total light output is staggering. This is a paradox. The star cools, and yet it brightens. It ages, and yet it becomes more magnificent. It approaches the end of its life, and yet it shines more brilliantly than it ever did in its youth. There is something almost hopeful about this, if you choose to see it that way. Or perhaps it is simply a reminder that the universe does not always follow our expectations, that endings can be bright, that transformation can lead to greater beauty. But you don't need to extract a lesson. You don't need to philosophize. Just let the image rest in your mind. A vast, glowing star, cool and red on the surface, but blazing with the light of thousands of suns. a beacon in the darkness, visible across light years of space. And let that light guide you gently into sleep, not with its intensity, but with its presence, a distant glow, reminding you that even in the quiet hours, there is beauty, there is light, there is peace. The star brightens, thousands of times the sun's luminosity, and you are allowed to simply close your eyes and rest. Arcturus, a K-type giant, shines 170 times brighter than the sun despite similar mass. Arcturus, say the name slowly. Arcturus. It sounds ancient, doesn't it? Like the name of a forgotten king or a long-lost city. And in a way, it is ancient. Arcturus is one of the brightest stars in the night sky, a golden-orange beacon visible in the constellation Boötes. If you live in the northern hemisphere and look up in the spring or summer, you can find it. Follow the arc of the Big Dipper's handle. It will lead you to Arcturus. It has been visible to humans for as long as humans have looked up at the sky. The ancient Greeks knew it. The Polynesians used it for navigation. The Inuit told stories about it. For thousands of years, Arcturus has been a companion in the night, a fixed point in the turning sky. But Arcturus is not fixed. Not truly. It is moving, fast by stellar standards. It is plunging to the galaxy at over 120 kilometers per second, a high-velocity star that will eventually leave our neighborhood entirely. But that journey will take tens of thousands of years. So for now, it remains where it's always been, bright golden and steadfast. Arcturus is a red giant. Well, technically it's a K-type giant, which means it's not quite as cool as the reddest giants. Its surface is around 4,300 Kelvin, giving it a warm orange-gold hue rather than deep red. But what makes Arcturus remarkable is its brightness. It shines 170 times more brightly than the Sunday 170 times, despite being only slightly more massive than the sun. It has not always been this bright. When it was younger, when it was on the main sequence, it would have been a modest star, similar in many ways to our own sun. But now, in its old age, it has swollen to 25 times the sun's diameter. Its surface is cooled, and yet, because of its enormous size, it blazes in the night sky, one of the brightest stars visible from Earth. If you place Arcturus where the sun is, its surface would extend nearly to the orbit of Mercury. The Earth would be bathed in its golden light, receiving 170 times more energy than we do now. It would be a very different world, a very different sky. But Arcturus is not here. It is 37 light years away, far enough that its light, though bright, is gentle, a single point of gold in the darkness, hanging above the horizon on a summer night. There is something comforting about Arcturus. It is a star you can see, a star you can point to, a star that has been there in that same place for your entire life and for the entire lives of your ancestors stretching back thousands of years. And it will be there tomorrow, and the night after that, and the night after that. Let Arcturus be a point of stability for you, a reminder that some things endure, that even in the vastness of the universe, even in the complexity of stellar evolution, there are stars you can rely on to be there, shining softly, waiting for you to look up. And now, in this moment, you don't need to look up. You can close your eyes. You can let Arcturus shine in your imagination, a golden point of light, warm and steady and patient, 170 times brighter than the sun. And yet, from here, just a gentle glow in the night, a companion, a guide, a reminder that you are not alone in the darkness. Let Arcturus watch over you as you drift into sleep. Let its light be a beacon, leading you gently into rest. Red giants span spectral types K, M, and sometimes G or S, with carbon stars adding unique molecular signatures. Now we wade into the alphabet soup of stellar classification. But don't worry, you don't need to memorize the letters. Just let them flow past you, like the names of colors in a language you don't speak. Stars are classified by their spectra, the patterns of light they emit, and astronomers use letters to categorize them. O, B, A, F, G, K, M. These letters represent a sequence from hottest to coolest. The Sun is a G-type star. Yellow, about 5,800 Kelvin on the surface. Red giants are usually K or M types. K-type giants are orange-red, around 3,500 to 5,000 Kelvin. M-type giants are deep red, around 2,500 to 3,500 Kelvin. But there are variations. Some giants are still in the G range, not quite cool enough to be orange, but cooler than they once were. These are stars in transition, stars that have just begun to swell and cool. And then there are the S-type stars. These are rare, unusual giants where the spectral lines reveal the presence of zirconium oxide instead of the more common titanium oxide. They are chemically peculiar, products of exotic nuclear reactions deep in their interiors. And then there are the carbon stars. Carbon stars are a special kind of red giant. In their cores and shells, nuclear fusion has produced enormous amounts of carbon. And as the star ages and loses mass, some of this carbon dredges up to the surface, changing the chemistry of the star's atmosphere entirely. Carbon stars have more carbon than oxygen in their atmospheres, and this creates entirely new molecules. Instead of titanium oxide or vanadium oxide, you get carbon-based molecules like C2, Cn, and even long chains of carbon atoms. These molecules absorb light in different patterns, creating a spectrum unlike any other kind of star. Carbon stars glow with a deep, sooty red, like the embers of a coal fire. Some are even surrounded by clouds of carbon dust, soot particles floating in space, absorbing starlight and glowing faintly in the infrared. There is something almost otherworldly about carbon stars. They are rare, strange, beautiful in their peculiarity. But you don't need to remember the difference between an S-type and a carbon star. You don't need to know what zirconium oxide is. Just let the variety wash over you. Let it remind you that even within the category of red giant, There is diversity. There is complexity. There's an entire landscape of stellar types, each one slightly different, each one unique. The universe is not simple. It is not uniform. It is a tapestry of variation, woven from the laws of physics and chemistry, producing stars in every shade of red and orange and gold. And in that complexity, there is beauty, and in that beauty, there is peace. Let the spectral types blur together. K, M, G, S, carbon stars. Let them be sounds, not facts. Let them drift past you like the names of constellations you've never learned. The stars are out there, glowing in their various hues, and you are here, safe, warm, drifting gently towards sleep. The spectrum fades, the letters dissolve, and all that remains is a soft, red glow of distant giants, burning patiently in the night. Their spectra reveal dense absorption lines from metals and molecules like titanium oxide. If you were to take the light from a red giant and spread it out into a spectrum, a rainbow of colors from red to violet, you would not see a smooth gradient. You would see a forest, lines, thousands of them, dark lines, cutting through the colors like shadows on a bright day. These are absorption lines. They form when light from the star's core passes through the star's atmosphere. Atoms and molecules in that atmosphere absorb light at very specific wavelengths, removing those colors from the spectrum. What reaches us is light with gaps, missing wavelengths, represented as dark lines. And in a red giant, the spectrum is crowded with these lines. Why? Because the cool atmosphere of a red giant is full of molecules and metals. Titanium oxide, vanadium oxide, iron, calcium, magnesium, sodium. Each one absorbs light at its own characteristic wavelengths, each one leaving its signature in the spectrum. Astronomers call this a forest of lines because there are so many and they are so dense that they overlap and blend together like trees in a thick wood. And this forest tells a story. It tells us the temperature of the star's atmosphere. It tells us the chemical composition. How much iron, how much carbon, how much oxygen. It tells us the pressure in the atmosphere, the density, even the motion of the gas. But to the casual observer, to someone simply looking at the spectrum without the tools to decode it, it is just a pattern, a complex, intricate pattern of light and shadow. There's something mesmerizing about these patterns. They are regular, yet chaotic, ordered, yet dense, like the grain of wood, or the veins of a leaf, or the ripples on a pond. And you don't need to understand what they mean. You don't need to identify which line belongs to titanium and which belongs to iron. You only need to know that they are there, that the light from every star carries information encoded in these dark lines, waiting to be read. Let the forest of absorption lines fill your mind, not as a puzzle to solve, but as a texture, a pattern, something to rest your thoughts on, the way you might rest your eyes on the bark of a tree or the surface of calm water. The lines are there, dense and intricate, and they ask nothing of you. They simply exist, a record of the star's nature, written in light. Let the patterns soothe you. Let the density become a background a static that drowns out other thoughts. Let yourself drift into the forest, losing yourself among the trees, among the lines, among the quiet shadows. The spectrum is dense. The lines are many, and you are allowed to simply let go and rest in complexity without needing to understand it. This forest of lines helps astronomers classify luminosity via features like the calcium-2 triplet. The calcium-2 triplet, 3 lines, 3 specific wavelengths in the near-infrared part of the spectrum, where ionized calcium absorbs light. To an astronomer, these 3 lines are a tool, a ruler, a way to measure the luminosity of a star without knowing its distance. Here's how it works. The strength of the calcium-2 triplet, how deep and dark the lines are, depends on the density and temperature of the star's atmosphere. A giant star with an enormous, puffy envelope has a lower surface gravity than a dwarf star of the same temperature. Lower gravity means lower density. Lower density means the calcium-2 lines appear weaker. A supergiant has even lower surface gravity, even lower density, even weaker lines. So by measuring the calcium-2 triplet, astronomers can distinguish between a dwarf, a giant, and a supergiant, even if they don't know how far away the star is. And once they know what kind of star it is, once they know its intrinsic luminosity, they can compare that to its apparent brightness in the sky and calculate its distance. This is the Bader-Weselink method, named after the astronomers who developed it, and it relies on these 3 small lines, hidden in the near-infrared, invisible to the naked eye but clear as day through a spectrometer. But let's step back. You don't need to remember the calcium-2 triplet. You don't need to understand the Bader-Weselink method. Let the technical details slide past you like water over stones. What matters is the idea that light carries information, that by studying the subtle patterns in the star spectrum, we can learn not just what the star is made of, but how large it is, how bright it is, how far away it is. The universe reveals itself through light, through wavelengths and absorption lines, and carefully measured intensities. And there's something almost magical about this, that we, tiny beings on a small planet, can look up at a star hundreds or thousands of light years away, collect its light, spread it into a spectrum, and read its secrets. We can know the star without touching it, without traveling to it, just by looking, just by measuring, just by understanding the language of light. Let this idea settle gently in your mind. The calcium-2 triplet, 3 lines, 3 wavelengths, a key to unlocking the distance to the stars. And let it remind you that even the most complex problems have solutions, that even the vast, unreachable stars can be understood, that the universe, for all its mystery, is not unknowable. But you don't need to know it tonight. You don't need to solve it. You only need to rest and let the stars keep their secrets for now. The triplet glows faintly in the infrared. The lines measure luminosity. And you You are allowed to simply close your eyes and drift, letting the light fade, letting the measurements dissolve, letting sleep find you in the darkness. MK classification splits them into luminosity classes 3 giants and I supergiants. The MK system, Morgan Keenan classification, named after the astronomers William Morgan and Philip Keenan, who developed it in the 1940s. It's a system for classifying stars based on their spectra, and it uses 2 pieces of information: spectral type, which tells you the star's temperature, and luminosity class, which tells you the star's intrinsic brightness. The luminosity classes range from I to V. Class 1, supergiants, the brightest, most luminous stars. Class 2, bright giants. Class 3, giants. Class 4, subgiants. Class V, main sequence stars like the Sun. Red giants fall into Class 3. They are luminous, but not as luminous as supergiants. They are large, but not as large as the largest stars in the galaxy. Supergiants fall into Class I. They are the titans of the stellar world, shining with the light of tens of thousands or even hundreds of thousands of suns. The distinction is important to astronomers because it affects everything else they want to know about the star: its distance, its age, its fate. But to you, in this moment, the distinction is not important. Let it be trivia. Let it be a footnote. Let the Roman numerals blur together. 1, 2, 3, just symbols, just categories. What matters is the idea that stars come in types, that they can be sorted, classified, arranged into groups based on shared properties. And there is something comforting about classification, about putting things in order, about knowing that even the chaotic night sky, with its thousands of stars scattered across the darkness, can be organized, can be understood, can be mapped. Astronomers have spent centuries classifying stars, building catalogs, creating systems, assigning each star a type, a class, a designation. And now, because of their work, we can look up at a star and say, that is AK3 giant. That is an M2IB supergiant. That is a G2V main sequence star like the Sun. We can give names to the stars. Not poetic names like Arcturus or Betelgeuse, but technical names. Names that describe their nature. And in that naming, there is power. There is understanding. There is the satisfaction of knowledge. But you don't need that knowledge tonight. You don't need to memorize the luminosity classes or the spectral types. Let them be sounds. Let them be patterns. Let them fade into the background as you drift deeper into rest. Class 3, giants. Class 1, supergiants. The stars are out there, classified and cataloged, glowing in their designated places. And you are here, safe, warm, allowed to let go of the need to classify, to organize, to understand. The MK system holds the stars, and sleep will hold you. Astronomers distinguish giants from supergiants using spectral tools like cyanogen band strengths. Cyanogen, it's a molecule, 2 atoms carbon and nitrogen bonded together. CN. It forms in the atmospheres of cool stars, and it absorbs light in very specific wavelengths, creating distinctive bands in the star spectrum. And here's the interesting part. The strength of these cyanogen bands depends on the star's surface gravity. A giant has relatively high surface gravity for its size. Its envelope is puffy, yes, but the star is massive enough that there is still significant gravitational pull at the surface. A supergiant has much lower surface gravity. Its envelope is even puffier, more extended, more diffuse. The gravity at the surface is weak, and this difference affects the cyanogen bands. In a giant, the cyanogen bands are stronger. In a supergiant, they are weaker. So by measuring the strength of these bands, astronomers can tell whether they are looking at a giant or a supergiant, even if the stars have similar temperatures and colors. It's a subtle difference, a matter of measuring the depth of a few spectral lines, comparing them to reference standards, calculating ratios. But it's enough. It's enough to distinguish between a star that is merely large and a star that is truly enormous. You don't need to remember what cyanogen is. You don't need to visualize the molecular structure or understand the chemistry. Just let the word rest in your mind. Cyanogen. Cyanogen. It sounds almost like a sedative, doesn't it? A chemical that induces calm, that slows the mind. Let it be that for you. Let the cyanogen bands be a lullaby, a technical detail so specific, so esoteric, that it fatigues your brain just to think about it. The bands are there, strong in giants, weak in supergiants, a tool for astronomers, a key to unlocking the nature of distant stars. And for you, just another piece of the vast, complex tapestry of stellar physics. Another thread in the weave, another note in the symphony. Let it blend into the background. Let it become part of the gentle hum of information that surrounds you, asking nothing, demanding nothing, simply existing. The cyanogen bands fade, the distinction blurs, and you are allowed to stop distinguishing, stop analyzing, stop thinking. Just rest, just breathe, just let the stars be stars, and let yourself be at peace. The calcium-2 triplet in near-infrared spectra refines distance estimates via the Bader-Wesselink method. We return to the calcium-2 triplet. 3 lines, 3 wavelengths, 3 windows into the nature of a star. The Bader-Wesselink method is a clever piece of astronomical technique. It allows astronomers to measure the distance to a star by combining spectroscopy with photometry, the study of how the star's brightness changes over time. Many red giants are variable stars. They pulsate, they expand and contract rhythmically like a slow heartbeat, and as they pulsate, their brightness changes. By measuring how the brightness changes and how the spectral lines shift due to the Doppler effect as the star's surface moves toward and away from us, astronomers can calculate the physical size of the star. And once they know the physical size and they know the apparent size, how large the star appears in the sky, they can calculate the distance The calcium-2 triplet is key to this method because it provides a reliable measure of the star's luminosity class, which helps refine the calculations. It's a beautiful piece of reasoning, a chain of logic that stretches from the absorption of light by calcium ions through the pulsation of the star's envelope to the final calculation of distance. But you don't need to follow the chain. You don't need to understand the math. You don't need to visualize the pulsations or the Doppler shifts. Just let the idea wash over you. The idea that light pulsation and spectroscopy can combine to reveal the distance to a star. The idea that we are not helpless in the face of the cosmos. That we have tools, methods, ways of knowing, and in that knowledge, there's comfort. The universe is vast, yes, but it is not chaotic. It follows rules. It reveals itself to patient observation and careful measurement. The calcium-2 triplet glows in the near-infrared. The Bader-Weselink method calculates distance. The stars are mapped, measured, understood, and you are allowed to let go of the need to measure, to calculate, to understand. You can simply be here, now, in the darkness, drifting gently towards sleep. The triplet fades, the method dissolves, and all that remains is the soft, warm glow of distant stars and the quiet embrace of rest. Let it hold you, let it carry you, let yourself drift like light through space toward the gentle, inevitable peace of sleep. Gaia mission catalogs millions of giants via precise parallaxes and colors. There is a spacecraft right now orbiting the sun. It is called Gaia, a European Space Agency mission launched in 2013, designed for a single purpose: to map the stars, not just a few stars, not just the brightest or the nearest, all of them, or at least as many as can be observed from a single vantage point in space. Gaia has cataloged over 1 billion stars. 1 billion. Each one measured with extraordinary precision. Each one assigned a position in the sky, a brightness, a color, and most importantly, a parallax. Parallax is the apparent shift in a star's position as the Earth and Gaia orbit the Sun. It's a simple geometric effect, the same as when you hold your finger at arm's length and blink one eye, then the other, your finger appears to jump against the background. For stars, the parallax is tiny, a fraction of a second of arc, but Gaia can measure it, and from that parallax, we can calculate distance. Among the billion stars in Gaia's catalog, millions are red giants. Gaia sees them scattered across the galaxy. Some are nearby in our local neighborhood. Others are thousands of light years away, on the far side of the galactic disk. Gaia measures their positions, their colors, their motions through space. And from this data, astronomers can study red giants as a population, not just individual stars, but entire groups. They can trace where red giants form, how they move, how they cluster in the spiral arms of the galaxy. There is something awe-inspiring about the scale of observation. Millions of stars, each one a sun in its own right, each one with its own history, its own journey through the stages of stellar evolution. And Gaia watches them all, patiently, continuously, recording their positions night after night, building a map of unprecedented detail and precision. You don't need to grasp the full scope of the Gaia mission. You don't need to understand parallax or astrometry. Just let the idea rest in your mind. A spacecraft drifting in orbit, measuring the stars, adding to the cosmic senses one observation at a time. Millions of giants, cataloged, mapped, known, and among them, somewhere, a star much like the sun will one day become. A future red giant, already visible to Gaia's sensors, already part of the great map of the galaxy. Let the scale of this wash over you. Millions of stars, billions of measurements, the patient, methodical work of science, unfolding in orbit above us. And let it remind you that you are small, that your worries are small, that the universe is vast and ancient and full of wonders that will continue whether you are awake or asleep. Gaia maps the stars. The giants glow in the catalog. And you are allowed to simply rest, knowing that the work of understanding the cosmos will continue without you. Let the spacecraft orbit. Let the parallaxes accumulate. And let yourself drift into the soft, measureless darkness of sleep. Infrared excesses flag dusty giants, probing mass loss histories. Some red giants are surrounded by dust, not the kind of dust you find on a shelf or under a bed. Cosmic dust, tiny grains of carbon or silicate, each one smaller than a particle of smoke, floating in the space around the star. This dust forms when the star loses mass. Red giants, especially as they age, shed their outer layers. The process is slow, gentle, a stellar wind, not unlike the solar wind that flows from the sun, but much denser, much richer in material. As this wind drifts away from the star, it cools. And in the cooling gas, atoms begin to stick together. Carbon atoms cluster. Silicon and oxygen combine to form tiny crystals of silicate. These are the seeds of dust. And once the dust forms, it absorbs light from the star. It heats up, glowing faintly in the infrared. This creates an infrared excess. More infrared light than you expect from the star's temperature alone. Astronomers can detect this excess. They compare the star's brightness in visible light to its brightness in infrared. And if the infrared is unusually strong, they know this star is dusty. This star is losing mass. And by studying the dust, they can probe the star's history. How much mass has it lost? How fast is it losing mass now? What will happen to this mass as it drifts into space? Some of it will disperse into the interstellar medium, enriching the galaxy with heavy elements. Some of it will eventually collapse to form new stars, new planets, new worlds. The dust from dying stars is the raw material for future solar systems. The carbon in your body, the iron in your blood, the calcium in your bones, all of it was forged in stars, expelled in stellar winds, scattered through space, and eventually incorporated into the earth. You are made of stardust, literally. But let's not dwell on that too much. Let the thought drift past you, like the dust itself, drifting through the void. What matters is the image, a red giant, glowing softly in visible light, surrounded by a faint halo of dust. The dust absorbs the star's light, warms and glows in the infrared, a gentle, invisible heat radiating into the darkness. There is no violence here, no explosion, just a slow, steady shedding of mass, the quiet formation of dust, the patient enrichment of the galaxy. Let the dust settle in your mind. Let it be a soft, diffuse cloud, glowing faintly, drifting outward, spreading into space. And let yourself drift with it. Let your thoughts disperse, scatter, dissolve into the warm, infrared glow of rest. The giants shed their mass. The dust glows. And you are allowed to let go, to release, to drift into the gentle, invisible embrace of sleep. Astroseismic grids from Kepler and Plato map internal structures across populations. Now we enter the realm of astroseismology, the study of stellar vibrations, the science of listening to the music of the stars. Stars are not static. They are not solid. They are vast spheres of gas, and like any gas, they can vibrate, they can oscillate, they can ring like bells. These oscillations are driven by turbulence in the star's convective envelope, the churning, boiling outer layers where heat is transported by the motion of gas rather than by radiation. This turbulence generates sound waves, which propagate through the star, reflecting off the surface and the core, creating standing wave patterns. And these patterns are detectable. The oscillations cause the star's brightness to vary ever so slightly. The star swells and shrinks, dims and brightens, in a complex rhythm governed by its internal structure. Spacecraft like Kepler and Plato have measured these variations for thousands of stars. They've collected data on the frequencies of oscillation, the amplitudes, the patterns of variation, and from this data, astronomers have built grids, vast data sets that map the internal structures of entire populations of red giants. Each star is a point in this grid. Each point represents a unique combination of mass, radius, core composition, envelope structure. And by comparing stars across the grid, astronomers can trace the paths of stellar evolution, seeing how giants change as they age, as they burn through their fuel, as they approach the end of their lives. There's something almost musical about astroseismology. The stars vibrate at specific frequencies, like the strings of an instrument. Some vibrations are high-pitched, others low. Some are simple, others complex, with multiple overtones blending together. And by analyzing these frequencies, we can hear the interior of the star. We can measure the density of the core, the thickness of the envelope, the speed of sound deep inside. We can probe regions that will never be directly visible, using only the faint, rhythmic variations in starlight. Let the idea of astroseismology settle gently in your mind. Stars vibrating, sound waves propagating through gas, frequencies measured with exquisite precision, revealing the hidden interiors of distant suns. You don't need to understand the math. You don't need to visualize the wave patterns. Just let the concept drift past you. Stars as musical instruments, each one ringing with its own unique tone. Kepler listened. Plato listens. The grids are built, point by point, star by star, mapping the symphony of the giants. And you are allowed to simply listen to the silence, to let the cosmic music fade into the background, to rest in the quiet space between the notes. The stars oscillate. The grids map their structures. And you are allowed to simply be still and let sleep find you in the stillness. Mixed modes act as P modes and envelopes and G modes and cores, exposing internal structure. There are two kinds of oscillations in a star, two types of waves that can propagate through the gas. P modes, or pressure modes. These are sound waves, literally. They are compression waves, like the vibrations in air that carry sound. In a star, P modes are driven by pressure gradients, and they propagate primarily through convective envelope, the outer, churning layers of the star. G modes, or gravity modes. These are buoyancy waves. They are driven by the restoring force of gravity, acting on parcels of gas that are displaced vertically. G modes propagate in regions where the gas is stably stratified, like the core of a red giant, where there is no convection, only smooth gradient of density and temperature. In most stars, P modes and G modes are separate. The P modes stay in the envelope. The G modes stay in the core. They don't interact. But in red giants, something special happens. The boundary between the convective envelope and the radiative core is not perfectly sharp. There's a transition region, a shell where the properties of the gas change gradually. And in this region, P modes and G modes can couple together. They create what are called mixed modes. A mixed mode behaves like a P mode in the envelope, oscillating with the rhythms of the convective turbulence. But it also behaves like a G mode in the core, sensing the density and temperature of the deep interior. And because of this dual nature, mixed modes are incredibly powerful tools for probing the internal structure of red giants. By measuring the frequencies of mixed modes, astronomers can determine the size of the core, the density of a helium that has accumulated there, the rate at which the star is burning hydrogen in the shell around the core. They can, in essence, see inside the star, not with light, but with sound. There is something almost poetic about this. The idea that waves can travel through a star, carrying information from the hidden depths, revealing secrets that would otherwise remain forever locked away. But you don't need to visualize the wave propagation. You don't need to understand the coupling mechanism. Just let the words wash over you. P modes, G modes, mixed modes, envelopes and cores. Let them be sounds, not concepts. Let them be part of the gentle hum of technical language that surrounds you, asking nothing, demanding nothing, simply existing as a soothing background. The modes mix, the waves couple, the structures exposed, and you are allowed to let the structure of your thoughts dissolve. to let the boundaries blur, to let yourself drift into a state where there is no distinction between waking and sleeping, only the gentle, rhythmic oscillation between the two. Let the mixed modes carry you. Let them propagate through your awareness, gentle and slow, revealing nothing, demanding nothing, simply being. And let sleep find you in the quiet spaces between the oscillations. Solar-like P modes and envelopes reveal surface gravity and mass via frequency spacing. The sun oscillates. This was discovered in the 1960s, when astronomers noticed that the surface of the sun was moving not dramatically, but measurably. Parts of the surface were rising, parts were sinking, in a complex pattern of oscillations. These are P modes, pressure modes, sound waves trapped inside the sun, bouncing between the surface and the deep interior, creating standing wave patterns that cause the surface to move up and down with periods of about 5 minutes. And it turns out many stars oscillate in the same way. Stars with convective envelopes, like the sun stars like red giants. We call these solar-like oscillations. The frequencies of these oscillations are not random. They follow a pattern. They are evenly spaced, like the rungs of a ladder, with a separation that depends on the star's surface gravity and mass. This spacing is called the large frequency separation, and by measuring it, astronomers can determine fundamental properties of the star. How massive it is, how large, how strong the gravity at its surface. It's a remarkable tool, a way to weigh a star from light years away, using only the faint rhythmic variations in its brightness. The sun's large frequency separation is about 135 microhertz. That's a very small number. 135 oscillations per million seconds. But it's measurable, and it tells us about the sun's structure. For red giants, the large frequency separation is smaller, much smaller, because red giants are larger, and the sound waves take longer to travel through them. The frequencies are lower, the spacing is tighter, but the pattern is the same, the physics is the same, and the information is there, encoded in the oscillations, waiting to be decoded. Let the idea of solar-like oscillations settle in your mind. The sun, humming with sound waves, red giants, oscillating in the same way, but slower, deeper, more resonant. You don't need to remember the numbers. You don't need to calculate the frequencies. Just let the concept drift past you. Stars as vibrating spheres, ringing with their own unique tones. The P modes oscillate. The frequencies are spaced. The mass and gravity are revealed, and you are allowed to simply resonate with the quiet rhythm of rest, to let your own oscillations slow, to let your own frequencies drop, to let yourself settle into the deep, low tones of sleep. The sun hums, the giants resonate, and you are allowed to simply be still and let the vibrations fade into silence. Gravity-dominated G modes probe core helium content and evolution stage. Deep inside a red giant, in the quiet, radiative core, gravity modes propagate. These are not sound waves. They are buoyancy waves. Waves that arise when parcel gas is displaced upward or downward, and gravity pulls it back toward equilibrium. Imagine a bubble in water. If you push it down, it rises back up. If you lift it, it sinks back down. This restoring force creates oscillations. The bubble bobs up and down, overshooting equilibrium each time, creating a wave. In a star's core, the same thing happens. Parcels of gas oscillate vertically, driven by the restoring force of gravity acting on density differences. These are G-modes, and G-modes are sensitive to the composition of the core. In a red giant, the core is made primarily of helium. This helium has accumulated over billions of years as hydrogen fused into helium in the core while the star was on the main sequence. Now, the helium just sits there, inert, unable to fuse because the temperature is not yet high enough. But the amount of helium in the core changes as the star evolves. As the hydrogen shell burns, more helium is added to the core. The core grows, the density increases, the temperature rises, and these changes affect the G-modes. They change the frequencies, the propagation speeds, the patterns of oscillation. By measuring G-mode frequencies, astronomers can determine how much helium is in the core. They can estimate the star's age. They can predict when the core will reach the critical temperature for helium fusion, the moment when the star will undergo the helium flash, a brief, dramatic ignition of helium burning that will propel the star into a new phase of evolution. But that moment is still far off. For now, the core is quiet. The helium waits. The G-modes propagate, carrying information from the depths to the surface, where it can be detected as faint variations in starlight. There is something deeply satisfying about this. The idea that we can probe the innermost regions of the star, regions that are invisible, unreachable, separated from us by light years of space and layers of dense gas. And yet, through the patient analysis of oscillations, we can know what is there. We can measure the helium content. We can trace the evolution. We can peer into the heart of a distant sun. But you don't need to peer. You don't need to measure. You don't need to understand the details of G-mode propagation or helium accumulation. Just let the idea drift past you. The core, quiet and heavy with helium. The G-modes, propagating slowly through the stratified layers. The information carried upward, revealed to patient observers. The core is probed. The helium is measured. The evolution stage is known. And you are allowed to simply rest in the knowledge that the universe is knowable, that the stars reveal their secrets, that nothing is truly hidden from careful observation. Let the G-modes fade. Let the core dissolve into abstraction. And let yourself sink gently into the deep, quiet darkness at the center of sleep. Dwarf giant discrimination uses large frequency separation exceeding 8 microhertz. 8 microhertz. It's a threshold, a dividing line, a way to tell from oscillation frequencies alone whether a star is a dwarf or giant. Dwarf stars, main sequence stars like the sun, are small, compact, dense. Sound waves travel through them quickly, and the frequencies of oscillation are high. The large frequency separation, the space in between adjacent P-mode frequencies, is typically greater than 8 microhertz. Giant stars are large, diffuse. The sound waves take much longer to traverse the star, and the frequencies are correspondingly lower. The large frequency separation is less than 8 microhertz. So by measuring this one number, this one spacing, astronomers can classify a star, dwarf or giant, small or large, dense or diffuse. It's a simple criterion, elegant in its simplicity. 8 microhertz, above or below. That's all you need to know. And yet, this simple number encodes so much information. It tells you about the star's size, its evolutionary state, its place in the cosmic cycle of birth and death. A star with a large frequency separation above 8 microhertz is young or middle-aged. It is burning hydrogen in its core. It is stable. It will remain on the main sequence for billions of years. A star with a large frequency separation below 8 microhertz has evolved. It has left the main sequence. It is a giant, swollen and luminous, approaching the later stages of its life. Let the number settle in your mind. 8 microhertz. A threshold between youth and age, between compactness and diffusion, between stability and transformation. You don't need to remember it. You don't need to understand why this particular value is a dividing line. Just let it be a marker, a signpost in the landscape of stellar evolution. Above 8, a dwarf. Below 8, a giant. And somewhere in the vast expanse of the galaxy, stars are oscillating at exactly this frequency, balanced on the threshold, neither fully dwarf nor fully giant, transitioning from one state to the other. Let the threshold blur, let the distinction fade. Let yourself drift into a state where categories lose their meaning, where boundaries dissolve, where there's only the gentle, continuous spectrum of being. 8 microhertz, a number, a threshold, a dividing line, and you are allowed to cross it, to drift from wakefulness into sleep, from thought into stillness, from awareness into deep, quiet rest that waits beyond all thresholds. The frequency separates, the classification is made, and you are allowed to simply let go and drift into the undifferentiated darkness. Astroseismic rotational splittings reveal core envelope decoupling. Stars rotate. The sun rotates once every 27 days at its equator. Red giants rotate too, though more slowly, and this rotation affects their oscillations. When a star rotates, the oscillation frequencies split. A mode that would have a single frequency in a non-rotating star splits into multiple frequencies in a rotating star, each one corresponding to a slightly different orientation of the oscillation pattern relative to the rotation axis. This is called rotational splitting, and by measuring the rotational splitting, astronomers can determine how fast the star is rotating. But here's where it gets interesting. in red giants, the core and the envelope can rotate at different rates. The core can spin much faster than the envelope. This is called differential rotation or core envelope decoupling, and the rotational splitting reveals this decoupling. The splitting pattern is more complex than it would be if the whole star were rotating as a solid body. There are extra frequencies, extra peaks in the oscillation spectrum that can only be explained if the core is rotating faster than the envelope. It's a subtle effect, a small deviation from the expected pattern, but it's measurable, and it tells us something profound about the internal dynamics of the star. The core and envelope are not rigidly connected. They can rotate independently, and this has implications for how angular momentum is transported inside the star, how magnetic fields are generated, how the star will evolve in the future. But let's not dive too deep into the physics. Let the idea drift past you, like the rotation itself, a slow, steady turning, the core spinning inside the envelope, each one following its own rhythm. Rotational splitting, core envelope decoupling, differential rotation. Let the terms blend together. Let them become a soft hum, a background murmur, part of the general tapestry of astroseismic complexity. The core spins. The envelope turns more slowly. The splitting reveals the difference, and you are allowed to decouple as well, to let your thoughts spin separately from your body, to let your awareness drift independently of your breathing, to enter that state where the mind and body are no longer rigidly connected, but float separately, each one settling into its own rhythm. Let the decoupling happen. Let the core of your being spin quietly, while the envelope of your awareness slows, stills, and drifts into the gentle rotation of sleep. The stars split, the rotation is measured, and you are allowed to simply turn slowly into the darkness. Cores spin 10 to 100 times faster than envelopes due to shell contraction and angular momentum conservation. 10 times faster, 100 times faster. The core of a red giant spins rapidly, much more rapidly than the envelope. This is one of the most striking discoveries of astroseismology. Why does this happen? The answer lies in a fundamental law of physics, conservation of angular momentum. Angular momentum is a measure of how much spin an object has. And in an isolated system, angular momentum is conserved. If an object shrinks, it spins faster. If it expands, it spins slower. This is why figure skaters spin faster when they pull their arms in. This is why a collapsing cloud of gas spins faster as it forms a star. And in a red giant, the core is contracting. Remember, after the hydrogen in the core is exhausted, gravity pulls the core inward. It shrinks. It grows denser. It heats up, and as it shrinks, it spins faster. The envelope, meanwhile, is expanding. It's growing larger, more diffuse, spreading outward. And as it expands, it spins slower. So over time, the core accelerates. The envelope decelerates. And the difference in rotation rates grows 10 times, 50 times, 100 times. The core becomes a rapidly spinning dynamo, hidden inside the slowly turning bulk of the star. And this differential rotation has consequences. It generates shear. It creates instabilities. It affects how energy and elements are mixed inside the star. But you don't need to trace the consequences. You don't need to understand the detailed physics of angular momentum transport. Just let the image settle in your mind. A core spinning rapidly, 100 times faster than the envelope that surrounds it. A hidden, whirling center buried deep inside the soft, slow-moving outer layers. There is something almost hypnotic about this image. The core spinning faster and faster, while the envelope drifts lazily around it. Two rhythms coexisting in the same star. Two timescales playing out simultaneously. Let this dual rhythm calm you. Let it remind you that things can move at different speeds, even within the same system. That fast and slow can coexist. That there is no single correct pace for anything. The core spins fast. The envelope spins slowly. And you are allowed to choose your own rhythm. To let some parts of you race, while other parts rest. To let yourself be complex, layered, differential. Or you can let it all slow down. Let the core decelerate. Let the envelope drift to stillness. Let the rotation fade until there is no spin at all. Just a quiet, motionless piece of sleep. The core spin rapidly. The envelopes lag behind. And you are allowed to simply stop spinning and rest. Splitting patterns map angular momentum transport inefficiencies in stellar interiors. Angular momentum should, in theory, be transported efficiently inside a star. If the core is spinning faster than the envelope, friction and viscosity should gradually even out the rotation. The core should slow down. The envelope should speed up. Eventually, they should reach the same rotation rate. But they don't. The observations show that the core continues to spin much faster than the envelope, even in old red giants. This means that angular momentum transport inside the star is inefficient. Something is preventing the core and envelope from coming into equilibrium. But what? That's one of the big questions in stellar astrophysics right now. Astronomers are using astroseismic data to map the inefficiencies. They're measuring the rotational splitting patterns in detail, comparing them to theoretical models. Try to understand what physical processes are at work. Is it magnetic fields? Are tangled magnetic field lines threading through the star, creating barriers to angular momentum transport? Is it stable stratification in the radiative zone between core and envelope? Is the gas too stably layered to allow mixing? Is it something else entirely? Some process we haven't thought of yet? The splitting patterns hold clues. Each pattern is a piece of the puzzle. And by collecting enough patterns from enough stars, astronomers hope to solve the mystery. But for you, right now, the mystery doesn't need to be solved. Let it remain a mystery. Let it be one of the many unanswered questions in the universe, drifting quietly in the background of your awareness. Angular momentum transport, inefficiencies, splitting patterns. core envelope coupling. Let the words wash over you. Let them be technical terms that you don't need to understand. Let them be part of the gentle, complex hum of astrophysics, asking nothing of you, demanding nothing. The transport is inefficient. The splitting reveals it. The mystery remains. And you are allowed to remain in mystery as well. You don't need to solve anything tonight. You don't need to understand. You don't need to map the inefficiencies of your own internal processes. You can simply be inefficient, perhaps, imperfect, asymmetric, with parts of you moving at different speeds, with angular momentum distributed unevenly, with mysteries that may never be fully resolved. And that's okay. That's beautiful. That's exactly as it should be. Let the splitting patterns fade. Let the angular momentum settle. And let yourself drift gently into the ineffable, unmappable territory of sleep. Red giant cores harbor intense magnetic fields of 30 to 100 kilogauss near the hydrogen-burning shell. 30 kilogauss. To put that in perspective, the Earth's magnetic field, the invisible force that protects us from solar radiation, that guides compasses, that creates the northern and southern lights, is about half a gauss at the surface. 30 kilogauss is 60,000 times stronger. 100 kilogauss is 200,000 times stronger. These are immense magnetic fields, powerful enough to affect the structure of matter, strong enough to alter the behavior of atoms, intense enough to trap charged particles, to channel plasma, to generate forces that can reshape the interior of a star. And they exist hidden deep inside red giants, near the hydrogen-burning shell, in the hot, dense layers where fusion reactions generate the energy that keeps the star shining. We cannot see these magnetic fields directly. They are buried too deep, shielded by thousands of kilometers of opaque gas. But we can infer their presence. We can detect their effects on the star's oscillations, on the way energy propagates through the interior, on the subtle asymmetries in the astroseismic data. The magnetic fields disrupt the clean, simple patterns we would expect. They break symmetries. They introduce complications. And these complications, when carefully analyzed, reveal the hidden dynamos at work in the stellar core. But how do these fields arise? How do they grow so strong? That's a question we'll explore in a moment. For now, just let the idea settle. Magnetic fields, 30 to 100 kilogauss, hidden in the core of a red giant, invisible but powerful, shaping the star's evolution in ways we are only beginning to understand. There is something almost mysterious about these fields. They are there but unseen, powerful but hidden, like a secret at the heart of every giant star, a force that operates silently, patiently, shaping outcomes from the shadows. Let this mystery calm you. Let it remind you that not everything needs to be visible to be real, that hidden forces can be powerful, that what lies beneath the surface is often more significant than what shows on top. The magnetic fields swirl in the core, 30 kilogauss, 100 kilogauss, invisible torrents of magnetic force. And you are allowed to rest in the knowledge that some things are beyond seeing, beyond knowing, beyond understanding. And that's okay. Let the magnetic fields hold the core. Let them shape the star from within. And let yourself be held, shaped, carried by forces you cannot see, the gentle, invisible pull of sleep. These fields disrupt dipole mode symmetry and oscillations. In a perfectly spherical, non-magnetic star, the oscillation modes have beautiful symmetries. A dipole mode, for instance, has a simple structure. The star bulges at the poles and contracts at the equator, or vice versa, in a regular, symmetric pattern. The oscillation looks the same whether you view it from the North Pole, the South Pole, or the equator. But when you add a magnetic field, the symmetry breaks. The magnetic field creates a preferred direction in space. It defines an axis, and oscillations that would have been symmetric in a non-magnetic star now behave differently depending on their orientation relative to this axis. A mode aligned with the magnetic field might oscillate at one frequency. A mode perpendicular to the field might oscillate at a different frequency. The clean, simple pattern splits into multiple components, each one slightly different. This is what astronomers observe in red giants. The oscillation frequencies don't fall into neat, symmetric patterns. There are deviations, asymmetries, extra peaks in the spectrum that can only be explained by the presence of magnetic fields in the interior. It's a subtle effect. The frequency shifts are small, but they're measurable, and they provide a window into the magnetic structure of the star's core. There is something almost elegant about this, the way symmetry breaking reveals hidden structure, the way deviations from the expected pattern point to deeper truths. In physics, symmetry breaking is often a sign that something interesting is happening, that new physics is at work, that the simple models are not enough, and we need to look deeper, think harder, consider more complex possibilities. But you don't need to think harder tonight. You don't need to analyze the symmetry breaking or decode the frequency patterns. Just let the idea drift past you. Symmetries broken, oscillations disrupted, patterns made complex by invisible magnetic fields. Let the disruption be a kind of lullaby. Let the broken symmetry remind you that perfection is not required, that asymmetry is natural, that deviations from the ideal are not failures, but signs of richness, of complexity, of hidden depths. The dipole mode split. The symmetry breaks. The magnetic field shapes the oscillations from within. And you are allowed to break symmetry too, to let go of the need for perfect balance, perfect alignment, perfect harmony, to drift into the asymmetric, imperfect, beautiful state of sleep. They likely arise from fossil fields amplified during core contraction. A fossil field. It's a poetic term for an ancient magnetic field. A field that was present in the star from the very beginning, inherited from the cloud of gas that collapsed to form the star billions of years ago. Not all stars have fossil fields, but some do, And if a star is born with even a weak magnetic field threading through its interior, that field can persist for the star's entire lifetime. It doesn't disappear. It doesn't decay. It's frozen into the plasma, trapped by the electrical conductivity of the stellar gas. This is called frozen-in field and magnetohydrodynamics. The magnetic field lines move with the gas, carried along as the star evolves. And when the core of the star contracts, when it shrinks as the hydrogen runs out, the magnetic field is compressed. Imagine a rubber band wrapped around a balloon. If you deflate the balloon, the rubber band gets tighter. The same thing happens with a magnetic field in a contracting core. The field lines are squeezed together. The field strength increases. This is called flux conservation. The total magnetic flux, the field strength times the area, remains constant. So as the area decreases, the field strength must increase. A weak fossil field of, say, 10 Gauss in a young star's core can be amplified to 10,000 Gauss, or even 100,000 Gauss, as the core contracts over billions of years. This is likely the origin of the intense magnetic fields in red giant cores. Not a dynamo actively generating new field, but an old fossil field amplified by the slow, inexorable contraction of the core. There is something deeply satisfying about this explanation. It connects the present to the distant past. It suggests that the magnetic field we observe today in a red giant is a relic, a preserved remnant of the star's birth, amplified and strengthened, but fundamentally unchanged. The star carries its history with it. The magnetic field is a memory, frozen in plasma, persisting across billions of years. Let this idea settle gently in your mind. Fossil fields, ancient magnetism, memories preserved in the cores of stars. You, too, carry your history. Memories amplified by time, by experience, by the contraction and expansion of your own life's journey. And like the fossil field, these memories persist, shaping you in ways you might not always recognize. But tonight, you don't need to examine your memories. You don't need to trace your history. You can simply let it be, let it rest, let it freeze like a magnetic field in plasma, quiet and unchanging. The fossil field amplifies, the core contracts, the magnetism intensifies, and you are allowed to simply rest in the presence of your own history without needing to analyze it, amplify it, or understand it. Let the field be frozen. Let the past be still. And let yourself drift into the timeless, memoryless peace of sleep. Measurements limit core field geometries to tangled configurations rather than simple dipoles. A dipole field is simple. It's the kind of magnetic field you see in a bar magnet, with a north pole and a south pole, and field lines that arc smoothly from one pole to the other. The Earth's magnetic field is approximately a dipole. So is the sun's, though it's more complicated. In a star, a dipole field would create a clean, organized pattern. The field lines would be smooth, regular, predictable. But the magnetic fields in red giant cores are not dipoles. They are tangled, The field lines twist and turn. They loop back on themselves. They form knots and braids in complex three-dimensional structures that bear no resemblance to the simple geometry of a dipole. How do we know this? From the asteroseismic data. The way the oscillations are affected by the magnetic field depends on the field geometry. A simple dipole will produce a specific, characteristic pattern of frequency shifts. But the observed patterns don't match that prediction. They're more complex, more irregular. The only way to explain the observations is to assume that the field is tangled, disordered, chaotic even, and this makes sense. The core of a red giant is a dynamic place. The gas is moving. Convection in the envelope above can send plumes of material sinking into the radiative zone. Differential rotation between core and envelope can shear the magnetic field, stretching and twisting it. Over time, a simple dipole field would become tangled. The clean geometry would give way to complexity. There is something almost comforting about this. The universe tends toward complexity, not simplicity. Toward disorder, not order. And that's not a failure. It's just the natural evolution of things. A tangled magnetic field is not broken. It's just evolved, matured, shaped by the history of the star. Let the image of tangled field lines fill your mind, not as a problem to solve, but as a texture, a pattern, something intricate and beautiful in its complexity. You don't need to untangle the field. You don't need to smooth out the knots. Just let it be. Let the complexity exist without judgment. And let your own thoughts tangle. If they want to, let them loop and twist. Let them become disordered, chaotic, complex. It doesn't matter. In sleep, there's no need for clean geometry. No need for simple patterns. Only the tangled, intricate, beautiful complexity of rest. The field is tangled. The geometry is complex. The measurements confirm it. And you are allowed to be tangled too. To let go of the need for simplicity, for order, for clean lines. Let the tangles hold you. Let the complexity embrace you. And let yourself drift into the knotted, woven fabric of sleep. Only about 8% of red giants show photospheric spots from surface magnetic activity. 8%. That's a small number. Out of every 100 red giants, only 8 show visible signs of magnetic activity on their surfaces. Spots, dark patches like sunspots, where the magnetic field breaks through the photosphere and suppresses convection, cooling the gas and creating a region that appears darker than the surrounding surface. On the sun, sunspots are common. They come and go in an 11-year cycle, driven by the solar dynamo, the process that generates and regenerates the sun's magnetic field. But on red giants, spots are rare. Why? One reason is that red giants have deep convective envelopes. The convection zone, the churning, boiling layer where heat is transported by the motion of gas, extends far into the star. And deep convection tend to suppress the kind of organized, large-scale magnetic fields that create spots. Another reason is that red giants rotate slowly. The envelope at least rotates slowly, and slow rotation means weaker dynamo action, less magnetic field generation. So most red giants have weak, tangled magnetic fields at the surface, fields that are too disorganized, too weak to create spots. But 8% do. 8% have stronger fields. 8% show spots, modulation in their light curves, signs of active magnetic dynamos. And these are often the red giants in binary systems, stars that have companions, that are tidally locked, that rotate faster than they otherwise would because of the gravitational pull of their partner. We'll talk about that more in a moment. For now, just let the number settle. 8%, a minority, a rare occurrence. Most red giants are quiet. Their surfaces are smooth, unspotted, unmarked by magnetic activity. They glow evenly, peacefully, without the drama of flares or spots or magnetic eruptions. There's something calming about this. The idea that most stars are quiet. That activity is the exception, not the rule. That the default state of a red giant is calm, steady, peaceful. Let this calmness wash over you. Let it remind you that you, too, are allowed to be quiet, to have a smooth, untroubled surface, to let the magnetic dramas of the day fade away, leaving only the even, peaceful glow of rest. 8% show spots. 92% do not. And you can choose which category to be in tonight. You can let the spots fade. Let the magnetic activity quiet. Let the surface of your awareness become smooth, calm, unmarked. The giants glow evenly. The spots are rare. The surfaces are quiet. And you are allowed to simply glow softly, peacefully as you drift into sleep. Binary red giants exhibit much stronger photometric modulation than single stars. A binary star system, two stars orbiting each other, bound by gravity, circling their common center of mass, locked in an eternal dance. Sometimes the stars are far apart, sometimes they're close. And when they're close, when the separation is small enough, the gravitational interaction between them can profoundly affect their evolution. Red giants in closed binary systems behave differently from isolated red giants. One of the most striking differences is in their magnetic activity. Binary red giants show much stronger photometric modulation. Their brightness varies more as they rotate because they have larger, darker spots on their surfaces. Why? The answer lies in tidal forces. When two stars orbit close to each other, the gravitational pull of each star on the other creates tides. Just like the moon creates tides in Earth's oceans, a companion star creates tides in the outer layers of a red giant. These tides can dissipate energy. They can slow the rotation of the stars, locking them so that they always show the same face to each other, just as the moon always shows the same face to Earth. But tidal locking also does something else. It synchronizes the rotation of the red giant's envelope with the orbital period, and this can speed up the rotation. Compared to what would be in an isolated star, Faster rotation means stronger dynamo action. Stronger dynamo means stronger magnetic fields. Stronger fields mean more spots. So binary red giants are magnetically active in a way that single red giants usually are not. There is something almost poignant about this. The companion star, simply by being there, by exerting its gravitational pull, changes the nature of the red giant. It makes it more active, more variable, more dynamic. Isolation brings calm. Companionship brings complexity. Is this a lesson? Perhaps. Perhaps not. Perhaps it's just a fact about stars with no deeper meaning. But let it settle in your mind anyway. The binary giants modulating in brightness, the spots rotating in and out of view, the magnetic activity driven by the presence of a companion. And let it remind you, if you want, that companionship changes us, that we are different when we are alone than when we are with others, that proximity creates forces, gravitational, emotional, magnetic, that shape us in ways we might not always recognize. But tonight, you are alone. Or, if you're not alone, you can choose to be isolated in your awareness. You can let the tidal forces dissipate. You can let the rotation slow. You can let the magnetic activity quiet. You can be like a single red giant, calm, quiet, glowing evenly in the darkness. The binary giants modulate. The companions exert their pull. The activity strengthens. And you are allowed to simply rest, untethered, unmodulated, in the quiet stillness of sleep. Tidal locking in close binaries boosts fields via elliptical instability. Elliptical instability. It's a fluid dynamics phenomenon. When a rotating fluid is subjected to tidal forces, the flow can become unstable. It can develop turbulence. It can generate motion that amplifies magnetic fields. In a red giant in a close binary system, the companion star's gravity doesn't just pull evenly. It pulls more on the near side of the giant than on the far side. And because the giant is rotating, this differential pull creates a time-varying distortion. The star gets squeezed, not in a circle, but in an ellipse. The equator becomes slightly elongated in the direction of the companion. And this elliptical distortion, combined with rotation, drives a fluid instability. Currents start to flow in the convective envelope. Eddies form. Turbulence develops. And turbulence can act like a dynamo. It can take weak magnetic fields and amplify them. It can create new fields where none existed before. This is the elliptical instability, a mechanism for generating strong magnetic fields in tidally locked binaries. It's a subtle, complex process. The mathematics involves nonlinear fluid dynamics, resonance conditions, energy transfer between different modes of motion. It's not simple, but the result is clear. Tidally locked red giants have stronger magnetic fields, more spots, more activity. You don't need to understand the mechanism. You don't need to visualize the elliptical distortion or the turbulent eddies. Just let the words drift past you. elliptical instability, tidal locking, dynamo amplification. Let them be sounds. Let them be part of the gentle, technical background, a murmur of astrophysics that asks nothing of you. The instability develops, the fields amplify, the activity increases, and you can choose stability. You can let the turbulence dissipate. You can let the eddies fade. You can release the tidal forces and drift into a state of circular, smooth, undistorted calm. No ellipses, no instability, no amplification, just a round, perfect piece of rest. The binaries are locked. The instability develops. The fields strengthen. And you are allowed to unlock, to stabilize, to let the magnetic dramas fade into the quiet, steady glow of sleep. Near UV excess in H-alpha, magnesium I, calcium 2-line depths probe chromospheric heights. The chromosphere. It's a thin layer in a star's atmosphere, above the photosphere, the visible surface, and below the corona, the super-hot outer atmosphere. The chromosphere is a transition region, a place where the temperature rises with altitude from about 4,000 Kelvin at the top of the photosphere to tens of thousands of Kelvin at the base of corona. And in this transition region, certain spectral lines are formed. H-alpha, the red line of hydrogen, formed when an electron drops from the third energy level to the second. Magnesium I, calcium 2. These are emission lines, glowing bright against the background spectrum. By measuring the strength of these lines, astronomers can probe the chromosphere. They can determine how high it extends above the photosphere, how hot it is, how much energy is being deposited there by magnetic fields or acoustic waves. A strong H-alpha line means a thick, bright chromosphere. A strong calcium 2 line means significant chromospheric activity. Red giants typically have weak chromospheres. Their atmospheres are extended, diffuse, cool. There's not much energy available to heat the chromosphere to high temperatures. But some red giants, the magnetically active ones, the ones with spots, have stronger chromospheres. The magnetic fields channel energy into the upper atmosphere, heating the gas, creating emission, and there's an excess in the near-ultraviolet part of the spectrum. 2. UV light emitted by the hot chromosphere, detectable with UV-sensitive instruments. All of this can be measured. All of this provides information about the star's magnetic activity, its rotation, its atmospheric structure. But let's not get lost in the details. Let the spectral lines blur together. H-alpha, magnesium I, calcium 2, near UV excess. Let them be colors: red, green, violet, hues in the spectrum of a distant star, each one carrying information, but none of them demanding your attention. The chromosphere glows faintly. The lines probe its height. The measurements reveal its structure. And you are allowed to simply glow faintly in your own chromosphere, the boundary between waking and sleeping. The transition region where awareness fades into rest. Let the spectral lines measure you. Let the probes detect your gradual shift from consciousness to unconsciousness. And let yourself drift upward, outward, into the tenuous, glowing layers of sleep. The chromosphere is probed. The heights are measured. The lines reveal the structure. And you are allowed to simply drift through that structure, rising gently into the warm, diffuse atmosphere of rest. Magnesium I and H-alpha depths correlate with solar-like oscillation amplitudes at fixed surface gravity. There's a relationship, a correlation, a pattern that astronomers have discovered by comparing spectroscopic measurements with astroseismic data. Stars with deeper magnesium I and H-alpha absorption lines, which indicates less chromospheric activity, tend to have larger oscillation amplitudes. Stars with shallower lines, more chromospheric emission, tend to have smaller oscillation amplitudes. This is true when you compare stars with the same surface gravity, same size roughly, same evolutionary state, but different levels of magnetic activity. Why does this correlation exist? It's not entirely clear. It might be that magnetic fields and convective envelopes suppress the oscillations. It might be that the turbulence that generates magnetic fields also damps the oscillation modes. It might be something else entirely, but the correlation is there. It's measurable. It's reproducible across large samples of stars. And this correlation is useful. It means that by measuring a star spectrum, by measuring the depths of a few spectral lines, you can estimate the star's oscillation amplitude. And from that, you can infer other properties: surface gravity, radius, mass. Is a shortcut, a way to learn about a star without needing to conduct a full astroseismic analysis. But you don't need to remember the correlation. You don't need to understand why it exists. Just let the idea drift past you. A relationship between spectroscopy and astroseismology. A connection between chromospheric activity and stellar oscillations. Two measurements, seemingly unrelated, that turn out to be linked. The universe is full of these connections, these correlations, these hidden relationships between things that seem independent. And there is something almost soothing about that. The idea that everything is connected, that no measurement is truly isolated, that the spectrum tells you about the oscillations, and the oscillations tell you about the interior, and the interior tells you about the evolution, and the evolution tells you about the future. It's all linked, all part of a coherent whole. Let this interconnectedness calm you. Let it remind you that you, too, are part of a larger pattern, connected to others, to the world, to the cosmos. But you don't need to trace all the connections tonight. You don't need to map the correlations. You can simply rest in the knowledge that they're there, invisible threads linking everything to everything else. The magnesium I line correlates with oscillation amplitude. The H-alpha depth reveals chromospheric activity. The patterns are measured, recorded, understood. And you are allowed to simply let the patterns be, to rest in the web of correlations without needing to analyze them. Let the lines correlate. Let the amplitudes vary. And let yourself drift into the interconnected, coherent, peaceful fabric of sleep. These links enable magnetic field estimates combining spectroscopy and three-dimensional models. By combining spectroscopic measurements, the depths of magnesium and H-alpha and calcium lines, with astroseismic data, the frequencies and amplitudes of oscillations, and with three-dimensional models of stellar atmospheres and interiors, astronomers can estimate the strength of magnetic fields in red giants. It's a multi-step process, a synthesis of different kinds of data, a careful comparison of observations with theoretical predictions. The spectroscopy tells you about the chromosphere. The astroseismology tells you about the interior. The 3D models connect the two, simulating how magnetic fields affect the atmosphere and the oscillations. By adjusting the field strength in the models until they match the observations, you can estimate the actual magnetic field in the star. It's not a direct measurement. It's an inference, but it's the best we can do with current technology. And the results are consistent with what we expect. Red giants have weak surface fields, typically a few Gauss or less, much weaker than the core fields, but still measurable, still significant. There is something deeply satisfying about this, the way different techniques, spectroscopy, astroseismology, theoretical modeling, come together to reveal a single truth: the strength of the magnetic field. No single measurement is enough, but together they paint a coherent picture. This is how science works, not through sudden insights or isolated discoveries, but through the patient accumulation of evidence, the careful synthesis of data, the gradual convergence on truth. Let this process calm you. Let it remind you that understanding comes slowly, that no single observation, no single thought, no single moment is enough to grasp the whole. You need patience. You need synthesis. You need to let the pieces come together in their own time. And you don't need to force it. You don't need to rush. You can simply let the data accumulate. Let the models refine. Let the estimate converge in its own time, at its own pace. The links enable estimates. The spectroscopy combines with models. The magnetic fields are measured indirectly, patiently, carefully. And you are allowed to let your own internal estimates drift, to let the measurements blur, to let the models fade. You don't need to know the field strength tonight. You don't need to synthesize the data. You can simply rest, unmeasured, unmodeled, in the magnetic embrace of sleep. The fields are estimated. The links are traced. The models converge. And you are allowed to simply let go and drift into the soft, unmeasurable peace of rest. Giant convection cells span thousands of kilometers across red giant surfaces. Imagine the surface of a red giant, not as a smooth, glowing sphere, but as a churning sea, a vast expanse of gas, roiling and bubbling, driven by heat from the interior. Convection cells, enormous parcels of gas, rising from the depths, expanding as they rise, cooling as they reach the surface, then sinking back down to be heated again. On the sun, convection cells are relatively small. The largest ones, called supergranules, are about 30,000 kilometers across. Still enormous by human standards, about twice the diameter of Earth, but small compared to the Sun's overall size. On a red giant, the convection cells are much larger. They can span thousands of kilometers, tens of thousands, even hundreds of thousands of kilometers across. Each cell is a titanic column of rising, cooling, sinking gas, larger than entire planets. Why are they so large? Because the red giant's convective envelope is so deep. It extends from near the surface down to the hydrogen-burning shell, encompassing most of the star's volume. And in a deep convective zone, the cells naturally organize into larger structures. There are fewer cells. They're bigger. They move more slowly. A convection cell on a red giant might take days or weeks to complete a full cycle. Rise, expand, cool, sink, heat, rise again. It's a slow, patient rhythm. The heartbeat of the star, played out on timescales far longer than human perception. And these cells create structure on the star's surface. Hot regions where rising gas brings heat from below. Cool regions where sinking gas drains warmth away. If you could see a red giant up close, you wouldn't see a smooth sphere. You'd see a mottled surface, divided into cells, each one glowing at a slightly different brightness, a slightly different temperature. There is something almost hypnotic about this image. The slow churning, the vast cells, the patient cycling of gas, up and down, hot and cool, over and over. Let this rhythm calm you. Let it become your rhythm, rising and falling, warming and cooling, cycling between wakefulness and sleep. The convection cells span thousands of kilometers. They churn slowly across the surface. They create patterns, models, variations in brightness. And you are allowed to churn slowly too. To rise toward wakefulness when you need to breathe, to sink toward sleep when you exhale, to cycle patiently, naturally, without hurry. Let the giant cells hold you. Let their slow rhythm become your rhythm. And let yourself drift into the deep, patient convection of rest. These cells create brightness flickers as hot gas bubbles rise and cool. As the convection cells rise and fall, the star's brightness changes. Not dramatically, not suddenly, but measurably. A hot bubble of gas rises to the surface. It's brighter than the surrounding gas. The star's total brightness increases slightly. The bubble cools. It darkens. It sinks back down. The brightness decreases. This creates a flicker, a variation in the star's light output. Irregular, because the convection is turbulent, chaotic. Different cells rising and falling at different times in different places. If you measure the brightness of a red giant over hours or days, you would see these flickers, small variations, typically a few percent, sometimes more, sometimes less. It's a form of noise in a sense. Random fluctuations driven by the turbulent motion of gas in the convective envelope. But it's also a signal. It tells us about the convection, about how deep it penetrates, about how fast the gas is moving, about the size and temperature of the cells. Astronomers study these brightness flickers. They measure them with high-precision photometry. They model them with computer simulations of stellar convection. And from this study, they learn about the interiors of red giants, about how heat is transported from the core to the surface, about how energy flows through the star. But you don't need to study the flickers. You don't need to measure them or model them. Just let the image rest in your mind. A star flickering, not like a candle in the wind, but slower, gentler, a slow waxing and waning of light as convection cells rise and fall. There's something calming about a flicker, a gentle variation, a reminder that nothing is perfectly steady, and that's okay. You flicker too. Your attention flickers. Your wakefulness flickers, rising and falling, brightening and dimming, as thoughts bubble up and sink away. And that's natural. That's how consciousness works. Not as a steady beam, but as a flickering flame. Let the flicker be part of your experience. Don't try to steady it. Don't try to hold the brightness constant. Just let it vary naturally as the convection cells of your mind rise and fall. The gas bubbles rise. The brightness flickers. The star varies gently, irregularly, naturally. And you are allowed to flicker too, to vary, to rise and fall, and eventually to fade into the steady, quiet darkness of sleep. Rotation modulates these spots, producing semi-regular light curves. As a red giant rotates, different parts of its surface come into view. If the surface is uniform, perfectly smooth, the brightness will be constant. You'd see the same amount of light, no matter which side of the star was facing you. But the surface is not uniform. It's modeled with convection cells. Some regions are hotter, brighter. Others are cooler, darker. So as the star rotates, the brightness varies. When a bright cell rotates into view, the brightness increases. When a dark cell rotates into view, the brightness decreases. This creates a semi-regular pattern in the light curve, the graph of brightness versus time. Semi-regular, because the pattern repeats with the rotation period. If the star rotates once every 100 days, the light curve will show variations with a period of roughly 100 days, but not perfectly regular, because the convection cells themselves are changing. They're not static features. They evolve, they merge, they split, they drift across the surface. So the light curve is modulated by rotation, but it's not a perfect sine wave. It's more complex, more irregular, more interesting. Astronomers can use this modulation to measure the rotation period of the star. They watch the light curve, looking for the characteristic timescale of the variations. And from that timescale, they infer how fast the star is spinning. Red giants rotate slowly. Periods of tens of days, hundreds of days. The envelope has expanded, and conservation of angular momentum has slowed the rotation to a crawl. But it's still measurable, still detectable in the light curve. Let the image of rotation settle in your mind. A giant star turning slowly, once every 100 days, once every 200 days, so slowly that you could watch for a week and see almost no change. But over time, the rotation is there, patient, inevitable, carrying bright cells and dark cells in and out of view. There is something deeply soothing about slow rotation. It's not frantic, not rushed, just a steady, patient turning, bringing change so gradually that it's barely perceptible. Let yourself rotate too. Let your awareness turn slowly, bringing different thoughts into view, then carrying them away again. Bright thoughts, dark thoughts, each one appearing, lingering, then fading as the rotation continues. And let the rotation slow. Let the period lengthen. Let the turn become so gradual that it's almost imperceptible, until finally the rotation stops. The light curve flattens, and there's only the steady, unchanging glow of sleep. The star rotates. The spots modulate the brightness. The light curve varies semi-regularly, patiently. And you are allowed to stop rotating, to let the modulation cease, to settle into the flat, steady calm of rest. Most exhibit irregular or semi-regular brightness changes, classified as SRC or LC variables. In the catalogs of variable stars, red giants occupy several categories. SRC variables, semi-regular variables of type C. These are red giants with periods of brightness variation ranging from tens to hundreds of days. The variations are somewhat regular, but not perfectly so. The amplitude changes from cycle to cycle. The period drifts slightly over time. LC variables, long period variables, irregular. These show variations over long time scales, months to years, but with no clear periodicity. The brightness rises and falls in a seemingly random fashion, driven by complex interactions between convection, rotation, and pulsation. Most red giants fall into one of these categories. They are variable stars. Their brightness is not constant. It changes over time in ways that can be measured, cataloged, studied. But the variations are gentle, subtle, nothing like the dramatic outbursts of a nova or the catastrophic explosion of a supernova. Just slow, patient changes. A few tenths of a magnitude, sometimes a full magnitude, occasionally more. If you watch a red giant for a month, you might notice it getting slightly brighter or dimmer. If you watch for a year, you'd see the full cycle of variation, rising, falling, rising again. There is something almost meditative about monitoring variable stars, measuring them night after night, recording the brightness, plotting the light curve, watching the pattern emerge over weeks and months. It requires patience, dedication, a willingness to wait for the slow rhythms of stellar evolution to reveal themselves. Let this patience seep into your awareness. Let it remind you that not everything happens quickly, that some patterns only emerge over long time scales. That understanding requires waiting, observing, allowing. You don't need to understand the classification system. You don't need to remember what SRC and LC stand for. Just let the idea drift past you. Variable stars, changing slowly, cataloged patiently by generations of astronomers. The giants vary. The brightness changes. The classifications are assigned. And you are allowed to vary too. To have nights when you're brighter, nights when you're dimmer. To change slowly, irregularly, without worrying about the pattern. Let the variation be natural. Let the irregularity be acceptable. And let yourself drift into the long, slow period of sleep. The SRC variables oscillate. The LC variables fluctuate. The light curves are recorded. And you are allowed to simply rest, unmeasured, uncatalogued, in the gentle, variable darkness. Amplitudes range from subtle flickers to form magnitudes, driven by convection cells or winds. For magnitudes, that's a large variation. A change in brightness by a factor of 40. A star that is 40 times brighter at maximum than at minimum. Most red giants don't vary this much. Most show variations of a few tenths of a magnitude, maybe one magnitude. Subtle changes, detectable with careful measurement but not obvious to the naked eye. But the mirror variables, the most extreme long period variables, can vary by 4 magnitudes or more. At maximum, they're bright enough to be easily visible. At minimum, they fade almost to invisibility, dropping below the limit of naked eye detection. This variation is driven by pulsation. The star literally swells and shrinks, expanding and contracting over periods of months or years. As it swells, the surface area increases and the brightness rises. As it contracts, the brightness falls. But convection and stellar winds also contribute. As the star pulsates, it drives mass loss. Gas is expelled from the surface, forming a shell or cloud around the star. This cloud can absorb and re-radiate light, adding complexity to the light curve. The interplay of pulsation, convection, and mass loss creates the rich variety of variability we observe in red giants. Some are stable, showing only tiny flickers. Others are wildly variable, changing dramatically over time. But even the most variable red giants change slowly, not from second to second, like a pulsar, not from minute to minute, like a flare star, but from week to week, month to month. You could watch a mirror variable for a single night and see almost no change. You'd need to observe it for months to see the full amplitude of variation. There's a lesson here, perhaps, that big changes take time. That dramatic transformations happen slowly. That patience is required to witness the full cycle. Or perhaps there is no lesson. Perhaps it's just a fact. Stars vary, some subtly, some dramatically, and the universe is richer for this diversity. Let the range of amplitudes wash over you, subtle flickers to form magnitudes. A vast spectrum of variability, all of it slow, all of it patient, all of it natural. And let yourself be variable too. Some nights, you'll fall asleep easily, quickly, with only subtle flickers of thought. Other nights, the variation will be larger. Thoughts will rise and fall more dramatically. And that's okay. You don't need to be constant. You don't need to be stable. You're allowed to vary within whatever amplitude is natural for you. The giant's flicker or pulse. The amplitudes range from subtle to extreme. The light curves are complex. And you are allowed to simply accept your own complexity, your own variability, and drift into the unchanging peace of sleep. Photospheric granulation causes small, truly irregular pulses in a few cases. Granulation on the sun. Granulation is the cellular pattern you see on the photosphere when you observe it through a telescope with high resolution. The surface is divided into tiny cells, each one a few hundred kilometers across, separated by darker lanes. These are the tops of convection cells. The bright centers are where hot gas rises. The dark lanes are where cool gas sinks. And because these cells are constantly evolving, forming, merging, disappearing, the brightness varies on very short time scales, seconds to minutes. This is photospheric granulation. The small scale, irregular flickering caused by turbulent convection right at the surface. Red giants show granulation too, though it's harder to observe because red giants are farther away and their surfaces are more extended. But with high-precision photometry from space missions like Kepler, astronomers can detect the irregular pulses caused by granulation, small variations in brightness, on timescales of hours to days, with no regular periodicity. These pulses are truly irregular, not semi-regular, like the rotational modulation, not quasi-periodic, like pulsations, just random noise, driven by the chaotic motion of gas in the photosphere. And yet, even this noise carries information. By analyzing the statistical properties of the granulation, the power spectrum, the time scales, the amplitudes, astronomers can learn about the surface gravity, the temperature, the turbulent velocity of the convective motions. Noise is never just noise. It's always a signal, if you know how to read it. But you don't need to read it. You don't need to analyze the granulation or extract information from the pulses. Just let the idea settle. Small, irregular flickering, truly random, driven by turbulence too complex to predict. There is something almost freeing about true irregularity. It means you can't plan for it. You can't anticipate it. You just have to accept it as it comes. Your thoughts, as you drift towards sleep, might become irregular, random pulses of awareness, disconnected images, fleeting sensations, no pattern, no structure, just noise. And that's okay. That's natural. That's the granulation of consciousness as it approaches the boundary of sleep. Don't try to organize it. Don't try to impose order. Just let the pulses come and go, random and irregular, fading gradually into stillness. The photosphere granulates. The pulses are irregular. The brightness flickers randomly, unpredictably. And you are allowed to be irregular too, to pulse randomly, to flicker without pattern. Until the granulation fades, the pulses cease, and there is only the smooth, quiet darkness of sleep. Radio pulsations over hundreds of days combine with longer non-radial modes. Some red giants pulsate, not rotating, not convecting, but pulsating. The entire star swells and shrinks rhythmically, driven by instabilities in the interior. Radio pulsations. The star expands radially outward in all directions, then contracts back inward. The surface moves up and down, like the membrane of a drum, creating waves of compression and rarefaction that propagate through the stellar envelope. These pulsations can have periods of hundreds of days. The star swells over the course of months, reaching maximum size, then contracts over the next few months, returning to minimum size, and the cycle repeats. Radial pulsations are the primary mode of variability in mirror variables and other long-period variables. They drive the large amplitude brightness changes, the mass loss, the dramatic transformations that occur in the final stages of red giant evolution. But radial pulsations are not the only kind. There are also non-radial pulsations. These are modes where different parts of the star move in different directions. Some regions expand while others contract. The star becomes distorted, elongated, asymmetric. Non-radial modes have their own periods, often longer than the radial modes, and they can combine with the radial pulsations, creating complex multi-periodic light curves. The interplay of radial and non-radial modes is still not fully understood. It's an active area of research in stellar astrophysics. Astronomers are measuring the periods, modeling the pulsations, trying to understand the physics that drives them. But for you, right now, the details don't matter. Just let the idea rest. Radial pulsations, non-radial modes, the star swelling and shrinking, distorting and relaxing, in a complex dance governed by gravity, pressure, and the structure of the stellar envelope. There's a rhythm to this, a slow, patient rhythm. Hundreds of days for a single cycle, years for the longer modes. Let this rhythm become your rhythm, expanding and contracting, swelling and shrinking, not physically, but in awareness, your consciousness expanding as thoughts arise, then contracting as they fade, and as the pulsations slow, as the amplitude decreases, let yourself settle into a state of equilibrium. No more expansion, no more contraction, just stillness. The radial modes pulsate, the non-radial modes distort, the periods combine, and you are allowed to simply stop pulsating, to let the modes damp, to settle into the quiet, stable equilibrium of sleep. Long secondary periods of 500 to 1500 days arise from radial-non-radial mode coupling. In some red giants, the light curve shows two periods. A primary period, typically a few hundred days, associated with radial pulsation, and a long secondary period much longer, 500 days, 1,000 days, 1,500 days, or more. For years, astronomers were puzzled by these long secondary periods. They didn't fit the simple models of radial pulsation. They were too long, too irregular, too strange. But recent work has suggested an explanation. The long secondary periods arise from the coupling between radial and non-radial modes. The radial mode pulsates at its own frequency. The non-radial mode pulsates at a different, lower frequency. And when these modes interact, when they exchange energy, interfere with each other, they create a beat pattern. A beat is what you hear when two musical notes are played at slightly different frequencies. The combined sound rises and falls in volume, creating a slow oscillation at the different frequency. The same thing happens in a pulsating red giant. The radial and non-radial modes create a beat, manifesting as a long secondary period in the light curve. It's a subtle, complex phenomenon. The mode coupling, the energy exchange, the creation of long period variability from the interaction of shorter period modes. And it's beautiful in a mathematical sense. The way two rhythms combine to create a third, slower rhythm. But you don't need to grasp the mathematics. You don't need to understand the mode coupling. Just let the idea drift past you. Two periods beating together, creating a long, slow variation. Let this image settle in your mind. Two rhythms, fast and slow, combining into something even slower. Your own rhythms are combining right now. The rhythm of your breath, the rhythm of your heartbeat, the rhythm of your thoughts, each one at its own frequency. And together, they create the long, slow rhythm of your descent into sleep. 1,500 days. That's over 4 years. A period so long that you'd need to observe a star for a decade to see the full cycle. But you don't need to wait a decade. Your long secondary period, the slow drift from wakefulness to sleep, takes only minutes or hours. Let the periods couple. Let the modes beat. Let the secondary rhythm emerge, slow and patient, carrying you deeper into rest. The long secondary periods arise. The coupling is measured. The beats are modeled. And you are allowed to simply let the periods lengthen, the coupling tighten, and the slow rhythm carry you into the timeless darkness of sleep. Mirrors like mirrors show 200 to 1,000 day fundamentals with overtone harmonics. Mira, it's a star, a specific star, the first variable star ever discovered, Omicron Ceti, located in the constellation Cetus, the whale. Mira was observed by ancient astronomers, who noticed that it varied in brightness. Sometimes it was visible to the naked eye, shining brightly in the night sky. Other times, it faded below the threshold of visibility, disappearing for months at a time. The name Mira means wonderful in Latin, and it is wonderful, a prototype, the first of a class of long-period variable stars, now known as Mira variables. Mira variables are red giants in the final stages of evolution. They pulsate radially with periods of 200 to 1,000 days. Their brightness varies by several magnitudes. They lose mass copiously, shedding their outer layers into space. They are approaching the end of their lives. Soon, in astronomical terms, which means thousands or tens of thousands of years, they will eject their envelopes entirely, leaving behind only the hot, dense core, a white dwarf. But for now, they pulsate, and their pulsations are complex. The fundamental mode is the primary pulsation. The entire star swells and shrinks in unison. But there are also overtones, higher frequency modes that add harmonics to the light curve, like a bell, which doesn't just ring at its fundamental frequency, but also produces overtones. Higher pitches that blend with the main tone. A mirror variable produces a complex sound, a blend of fundamental and harmonics. And this complexity can be measured, analyzed, modeled, but you don't need to analyze it. Just let the name settle. Mirror, the wonderful, a star that has been pulsating for millions of years, visible to humans for thousands of years, studied by astronomers for centuries, and it will continue to pulsate long after you've fallen asleep, long after you've woken up, long after your lifetime has passed. Let this continuity calm you. The stars continue. The pulsations continue. The universe carries on, patient and unhurried, whether you are awake or asleep. Mirror pulsates. The fundamental mode drives a variation. The overtones add harmonics. And you are allowed to simply rest in the presence of this ancient, pulsating star, to let its slow rhythm become part of the background, to let it remind you that you are part of a universe that is vast, old, and patient. Let mirror pulse. Let the harmonics blend, and let yourself drift into the fundamental, unchanging silence of sleep. These drive mass loss spikes, transitioning giants to protoplanetary nebulae. The pulsations of a mirror variable are not gentle. They are violent in the context of a red giant. The star swells to enormous sizes, then contracts dramatically. The surface accelerates outward, then crashes back inward. The motion is so extreme that it drives shocks, supersonic compression waves that propagate through the stellar atmosphere. And these shocks lift material off the surface. Gas that was once part of the star is accelerated outward by the pulsation. It escapes the star's gravity. It drifts into space, forming a shell or cloud around the star. This is mass loss. And for mirror variables, it can be extreme. They can lose the mass of the Earth every year, the mass of Jupiter every 1,000 years. Over time, they shed a significant fraction of their total mass. And this mass loss transforms the star. The outer envelope is gradually removed. The radius shrinks. The surface temperature increases. The star moves off the red giant branch and begins its transition toward becoming a white dwarf. But there is an intermediate stage. After the red giant phase, but before the white dwarf phase. This is the protoplanetary nebula phase. A protoplanetary nebula is not yet a true planetary nebula. The core is not yet hot enough to ionize the ejected material, but the envelope has been shed and the star is surrounded by a vast cloud of gas and dust, glowing faintly in the reflected light of the central star. This phase is brief, a few thousand years, a blink of an eye in cosmic terms, but it is a crucial transition, the bridge between the red giant and the white dwarf, driven by the pulsations, driven by the mass loss, driven by the slow, patient evolution of a dying star. There is something almost poignant about this. The star shedding its outer layers, transforming, preparing for the next phase. It is an ending, yes, but also a beginning. The material ejected by the star will enrich the interstellar medium. It will eventually become part of new stars, new planets, perhaps even new life. Nothing is truly lost. Everything is recycled. The universe is a closed loop of matter and energy, endlessly transforming. Let this idea settle gently in your mind. Mass loss, transition, transformation. You too are in transition, from waking to sleeping, shedding the layers of the day, letting go of thoughts, worries, plans, preparing for the next phase. And like the star, you will emerge renewed, the white dwarf phase of deep sleep, the restoration, the quiet, stable core that will shine again tomorrow. The pulsations drive mass loss, the giants transition, the protoplanetary nebulae form, and you are allowed to transition to shed the envelope of wakefulness, to drift into the quiet nebulous space between consciousness and unconsciousness. Let the mass loss carry away your thoughts. Let the transition unfold naturally, and let yourself drift into the protoplanetary nebula of sleep, diffuse, glowing faintly, suspended between one state and another. Soon, you will reach the core, the white dwarf of deep rest. But for now, just drift, just transition, just let go. Red giants lose 10 to the -7 to 10 to the -4 solar masses per year through dynamic chromospheres. A wind, not like the wind on Earth, made of air molecules rushing from high pressure to low pressure, but a stellar wind, a continuous outflow of gas from the star's atmosphere into space. The sun has a wind, the solar wind, a stream of charged particles, protons, electrons, helium nuclei, flowing outward at hundreds of kilometers per second. The solar wind fills the solar system, creating the heliosphere, a bubble of solar influence that extends far beyond the orbit of Pluto. But the solar wind is gentle. The sun loses only about 1 million tons of mass per second through the solar wind. That sounds like a lot, but in cosmic terms, it's negligible. At this rate, it would take trillions of years for the sun to lose even 1% of its mass. Red giants, in contrast, have much stronger winds. They lose anywhere from 10 to the -7 to 10 to the -4 solar masses per year. That's anywhere from 1/10,000,000th to 1/10,000th of the sun's mass per year. At the upper end of that range, a red giant could lose the mass of the sun in just 10,000 years. In 1,000,000 years, it could shed a significant fraction of its total mass. This is not negligible. This is substantial. This is a process that fundamentally alters the star's evolution. The wind is driven by the chromosphere, that thin, hot layer above the photosphere where energy is deposited by acoustic waves and magnetic fields. The gas in the chromosphere is heated to tens of thousands of degrees, hot enough to escape the star's gravity, and it flows outward, continuously, patiently, carrying mass away from the star, enriching the space around it. There is something almost generous about this. The star giving of itself, shedding its substance into the void, not holding on, but letting go. Let this image settle in your mind. A stellar wind, a continuous outflow, the star losing mass, year after year, century after century. And let it remind you that letting go is natural, that shedding what you no longer need is not a loss, but a transformation. The red giants lose mass, 10 to the -7th solar masses per year, 10 to the -4th, a continuous wind, flowing outward, carrying substance into space. And you are allowed to let things flow away from you. Thoughts, worries, the accumulated weight of the day. Let them drift outward, carried by your own internal wind, into the space beyond consciousness. The chromosphere drives the wind. The mass flows away. The star sheds itself. And you are allowed to shed too. To let go, to release, and to drift into the quiet, weightless freedom of sleep. This dust-driven wind forms molecular outflows observable in carbon monoxide emission. As the stellar wind flows outward, the gas cools, and in the cooling gas, atoms begin to combine. Carbon and oxygen form carbon monoxide. CO. Carbon and hydrogen form methane, CH4. Silicon and oxygen form silicon monoxide, CO. These are molecules. Complex structures form from the atoms forged in the star's interior and expelled in the wind. And these molecules emit light, not visible light, but radio waves, specific wavelengths in the millimeter and submillimeter part of the spectrum, corresponding to the rotational transitions of the molecules. Carbon monoxide is particularly bright. The CO molecule rotates, and as it transitions between rotational states, it emits photons at very specific wavelengths. These photons can be detected by radio telescopes on Earth. And by mapping the CO emission around a red giant, astronomers can trace the molecular outflow. They can see where the wind is flowing, how fast it's moving, how dense it is, how the molecules are distributed in space. It's a way of making the invisible visible. The stellar wind is too thin, too diffuse, to be seen directly in visible light, but the CO emission reveals it, painting a picture of the outflow in radio waves. There is something almost poetic about this. The star speaks in molecules, in the language of carbon and oxygen, bonded together, rotating, emitting faint radio whispers into the cosmos. And we listen. We point our radio telescopes at the stars. We collect the photons. We decode the message. The outflow is moving at 10 kilometers per second, 20 kilometers per second. Not fast by cosmic standards, but steady, patient. A gentle breeze carrying molecules into the interstellar medium. Let this image drift through your mind. Molecular outflows, carbon monoxide, radio emission from rotating molecules. You don't need to understand the quantum mechanics of rotational transitions. You don't need to visualize the molecular structure. Just let the idea be there. The star, speaking in molecules. The wind, carrying them outward. And let your own thoughts flow outward too. Let them become molecules. Simple, fundamental, rotating gently in the space of your awareness, emitting their faint signals, then drifting away. The wind forms molecular outflows. The CO emission is detected. The structure is mapped. And you are allowed to simply flow, to let your consciousness become molecular, diffuse, spread out into the space beyond thought. Let the molecules drift. Let the outflow carry them away. And let yourself dissolve into thin, gentle wind of sleep. Pulsation-enhanced, dust-driven winds accelerate outflows to 10 to 20 kilometers per second. The pulsations of a red giant don't just make the star brighter and dimmer. They don't just drive the variations in the light curve. They also enhance the stellar wind. Here's how it works. As the star pulsates, it lifts material off the surface. The outward motion during the expansion phase accelerates gas to higher velocities. And in the cool, dense layers above the photosphere, this gas can form dust, tiny grains, silicates, carbon particles, oxides, each grain smaller than a particle of smoke, but large enough to absorb and scatter light. And when light from the star hits these dust grains, it exerts a force, radiation pressure. The photons carry momentum, and when they're absorbed by the dust, that momentum is transferred to the grain. The dust grain accelerates outward, pushed by the radiation pressure, and the dust grain collides with gas molecules. It drags them along. The gas couples to the dust, and together they accelerate. This is the dust-driven wind. And in a pulsating red giant, it can be very efficient. The pulsations create the dust. The radiation pressure accelerates the dust. The dust drags the gas. And the whole wind accelerates to 10 or 20 kilometers per second. That's fast enough to escape the star's gravity. Fast enough to carry mass into the interstellar medium. Fast enough to strip the star of its outer layers over the course of thousands or tens of thousands of years. There is a beautiful synergy here. Pulsation, dust formation, radiation pressure, gas-dust coupling. Each process feeding into the next, creating a self-sustaining wind that gradually transforms a star. Let this synergy calm you. Let it remind you that complex systems can arise from simple interactions. That acceleration doesn't require force. just a patient accumulation of small pushes. The photons push the dust drags the gas, the wind accelerates, and you are allowed to be accelerated too. Not violently, not suddenly, but gently, patiently, pushed by the accumulated weight of the day toward the escape velocity of sleep. The pulsations enhance the wind. The dust drives the outflow. The velocity reaches 10-20 kilometers per second, and you are allowed to simply let go, to be lifted, to be carried, to accelerate gently into the outflow of rest. Let the radiation pressure push you. Let the dust drag you along, and let yourself flow outward, away from the star of wakefulness into the cool, dark void of sleep. Radiation pressure on dust grains couples the gas, sustaining high rates. Radiation pressure, it's a force we don't experience in daily life. The force of light, the push of photons. When light hits an object, it exerts a tiny force. For large objects on Earth, this force is negligible, overwhelmed by gravity and friction. But in space, where objects can be very small and very light, radiation pressure matters. A dust grain, a millionth of a meter across, floating in space around a red giant, feels the push of starlight, billions of photons per second, each one carrying a tiny amount of momentum, hitting the grain, being absorbed or scattered, and the grain accelerates, slowly at first, but steadily. The photons keep coming, and the force keeps pushing, and the grain picks up speed. 10 meters per second, 100 meters per second, a kilometer per second, 10 kilometers per second. And as the grain moves, it collides with gas molecules. Hydrogen, helium, carbon monoxide. Each collision transfers momentum from the grain to the gas. The gas accelerates. It couples to the dust, and together they form the stellar wind, driven outward by the steady, patient pressure of starlight. This is a remarkable process. The star's own light drives its own mass loss. The photons emitted by fusion reactions in the core eventually push material off the surface, reducing the star's mass, altering its evolution. It's a feedback loop, a self-regulating system. The more luminous the star, the stronger the radiation pressure, the faster the wind. And the wind, in turn, affects the star's structure, its temperature, its future evolution. There is something deeply satisfying about this. The elegance of the physics, the way light and matter interact, the way small forces, accumulated over time, can have dramatic effects. Let this elegance wash over you. Let it remind you that small, persistent forces can move mountains, that patience and consistency are more powerful than sudden bursts of effort. The photons push the dust couples to the gas, the wind is sustained, and you are allowed to be moved by small, persistent forces too. The gentle pressure of fatigue, the accumulated weight of the day, the steady, patient pull of sleep. You don't need to fight it. You don't need to resist. Just let the radiation pressure of rest push you gently, consistently, outward from wakefulness into sleep. Let the photons do their work. Let the coupling happen. Let the wind carry you away. Episodic ejections form concentric shells visible in scattered light. The stellar wind is not always steady. Sometimes it's strong. Sometimes it's weak. The mass loss rate varies with the pulsation, with the convection, with the activity of the star. And when the wind varies, it creates structure. Imagine a strong pulse of mass loss, a brief period, perhaps a few years, where the wind is particularly intense. A shell of gas and dust is ejected, moving outward at 10 or 20 kilometers per second. Then the wind weakens. The mass loss rate drops. The next shell of material is ejected more slowly or is less dense. Over time, the fast shell overtakes the slow shell. They collide. They compress. They create a dense ring of material, moving outward through space. And if this process happens repeatedly, if the star ejects shells episodically every few decades or every few centuries, the result is a series of concentric shells, nested spheres of gas and dust, spreading outward from the star like ripples on a pond. These shells can be seen, not in visible light usually. They're too diffuse, too faint. But in scattered light, in the infrared, in radio emission from molecules, the shells are visible. They're beautiful, symmetric, layered, a record of the star's history, written in concentric rings of expelled material. Astronomers study these shells. They measure their spacing, their velocities, their densities, and from this, they learn about the variability of the stellar wind, the timescales of mass loss, the mechanisms that drive the ejections. But you don't need to study them. Just let the image rest in your mind. Concentric shells, ripples spreading outward, a star shedding its substance in pulses, creating patterns in the void. There's something almost meditative about this image. The regularity, the symmetry, the patience of the process, playing out over centuries. Let the shells be a visual mantra. Concentric, expanding, layered, and let your own thoughts form shells, if they want to, layers of awareness, spreading outward, each one a little more diffuse, a little farther from the center, until there is nothing left but the faintest ripple at the edge of consciousness. The ejections form shells. The scattered light reveals them. The patterns are measured, and you are allowed to simply spread outward in concentric layers, each one fainter than the last, until you dissolve completely into the darkness of sleep. Strong winds erode atmospheres, enriching space with heavy elements. The stellar wind is not just a curiosity. It's not just an interesting astrophysical phenomenon to study. It has consequences, profound consequences. The wind erodes the star's atmosphere. It strips away the outer layers. The envelope that took billions of years to accumulate is removed in thousands or tens of thousands of years. The star loses mass. Its radius shrinks. Its luminosity decreases. Its structure changes. Eventually, the entire envelope is gone. Only the core remains, a hot, dense, naked core, a white dwarf. But the matter that was removed doesn't disappear. It spreads into space. It enriches the interstellar medium. And this matter is not just hydrogen and helium. It's enriched with heavy elements: carbon, nitrogen, oxygen, iron, silicon, all the elements forged in the star's interior through nuclear fusion. These elements are rare in the universe. Most of the universe is still hydrogen and helium, left over from the Big Bang. Heavy elements are created only in stars, through fusion reactions in cores and shells. And when a red giant sheds its envelope, it scatters these heavy elements into space. It enriches the interstellar medium. It provides a raw material for future generations of stars and planets. Without this process, without the winds from red giants, the universe would be depleted of heavy elements. There would be no carbon for organic molecules, no oxygen for water, no iron for planetary cores. Life as we know it depends on the enrichment of space by stellar winds. There is something almost profound about this: the generosity of dying stars, the way they give back to the cosmos, the cycle of birth, life, death, and rebirth played out on a galactic scale. Let this idea settle gently in your mind. The winds erode the atmospheres. The heavy elements are released. Space is enriched. And let it remind you that endings are not failures, that letting go is not loss, that what we release can become the foundation for something new. The red giants erode. The atmospheres are stripped. The heavy elements spread. And you are allowed to erode too, to strip away the layers of the day, to release the heavy elements of thought and worry into the space around you. What you let go will not be lost. It will enrich the space of your rest. It will become part of the foundation for tomorrow's renewal. Let the wind erode. Let the atmosphere strip away. And let yourself become lighter, simpler, reduced to the essential core sleep. Red giants forge cosmic dust grains from silicates, carbon oxides, and cool outflows. In the cool, dense regions of the stellar wind, far from the star's surface, something remarkable happens. Atoms begin to stick together, not forming molecules this time, but forming solids, tiny grains of matter. Dust, silicate dust, silicon and oxygen atoms bonding together, forming the same kind of minerals you find in sand on Earth: pyroxene, olivine, tiny crystals, each one a few millionths of a meter across. Carbon dust, carbon atoms clustering together, forming graphite or amorphous carbon. Soot, essentially, the same material you'd find in a candle flame, but formed in the outflow of a dying star. Oxide dust, aluminum oxide, magnesium oxide, calcium oxide, compounds formed from metals and oxygen, solidify in the cool wind. This is the forge, the place where cosmic dust is created. Not in the star's core, where temperatures are millions of degrees. Not on the star's surface, where it's still too hot for solids. But in the outflow, hundreds or thousands of stellar radii away, where the temperature has dropped below a few thousand degrees, cool enough for atoms to bond, cool enough for grains to nucleate, cool enough for dust to form. And once the grains form, they grow, atoms and molecules stick to the surface. The grains become larger. Some grow to 1/10 of a micron, some to a full micron, tiny but large enough to scatter light, to absorb radiation, to be pushed by radiation pressure into the interstellar medium. This dust is the stuff of planets, of asteroids, of comets, of you, the silicon in computer chips, the carbon in DNA, the oxygen you breathe. All of it was forged in stars, expelled in winds, condensed into dust grains, and eventually incorporated into the earth. You are made of star dust, not metaphorically, literally. Let this truth settle in your awareness. You are the product of red giant winds, of dust formation and stellar outflows, of cosmic recycling. And let it remind you that you are part of an unbroken chain of transformation, from stars to dust to planets to life. And now, as you drift towards sleep, you continue that transformation, from waking to sleeping, from thought to stillness, from complexity to simplicity. The red giants forge dust, silicates, carbon, oxides, tiny grains in cool outflows, and you are allowed to simply be a temporary coalescence of star dust, returning for a few hours to the formless, thoughtless state that preceded consciousness. Let the dust form, let the grains nucleate, and let yourself dissolve into the primordial matter of rest. This dust seeds molecular clouds for new stars and planets. The dust grains drift through space, not quickly, perhaps 10 or 20 kilometers per second, slow by cosmic standards, but steadily, patiently, away from the red giant that created them, into the vast expanse of the interstellar medium. And there in the cold, dark regions between the stars, the dust grains encounter gas, hydrogen, helium, traces of other elements. And something remarkable happens. The dust grains become seeds. Molecules form on their surfaces. Hydrogen atoms land on the grain, stick to it, find each other, and bond together, forming molecular hydrogen. H2, carbon monoxide forms. Water ice accumulates. The grain becomes coated with molecules, and the molecules attract more gas, and the gas begins to clump around the dust grains. Over millions of years, these clumps grow, they merge, they become denser, and eventually they collapse under their own gravity, forming new stars. The dust from red giants seeds the molecular clouds. It provides the nucleation sites for star formation. Without dust, the process would be much slower, much less efficient. And around these new stars, the leftover dust and gas form planets. The same dust grains that were forged in a red giant's wind become part of a planet's mantle. its atmosphere, its oceans. It's a cycle. Stars create dust. Dust creates stars. Stars create dust. On and on for billions of years. You are part of this cycle. The atoms in your body were once part of a red giant. Before that, they were part of a molecular cloud. Before that, they were part of an even older generation of stars. And after your atoms are returned to the earth, they will eventually become part of new stars, new planets, perhaps new life. Nothing is created. Nothing is destroyed. Everything is transformed. Let this cycle calm you. Let it remind you that you are not separate from the universe. You are the universe, temporarily organized into a form that can think and feel and wonder. And when you sleep, you return briefly to the formless state, the molecular cloud of unconsciousness, the seed state from which waking emerges. The dust seeds molecular clouds. The clouds collapse. New stars form. And you are allowed to collapse too. To let the structure of wakefulness dissolve. To become formless, seedful potential. Let the dust drift. Let the clouds gather. And let yourself become the seed of tomorrow's awakening, resting in the dark, fertile void of sleep. Carbon stars glow redder, dominating long-wavelength infrared skies. Not all red giants are the same. We've talked about this before. Spectral types, K, M, S, and carbon stars. Carbon stars are special. They're red giants that have dredged up enormous amounts of carbon from their interiors. Their atmospheres have more carbon than oxygen, and this changes everything. Instead of silicate dust, they form carbon dust. Soot, graphite. The dust is darker, more opaque. It absorbs visible light efficiently, making the star appear redder, and the dust re-radiates the absorbed energy in the infrared, long-wavelength infrared, beyond what the human eye can see, but detectable with infrared telescopes. If you looked at the sky with an infrared telescope, carbon stars would stand out. They would dominate the long-wavelength infrared sky, glowing brightly in wavelengths around 10 microns, 20 microns, 100 microns. They're beacons in the infrared. Cool, dusty, ancient stars nearing the end of their lives, shrouded in clouds of carbon soot. And they're beautiful in their own way. Not the sharp, brilliant beauty of a hot, young star, but the deep, smoldering beauty of embers, of charcoal, of twilight. Carbon stars are rare. Most red giants are oxygen-rich, forming silicate dust. But the carbon stars that do exist are fascinating. They represent a specific stage of evolution, a specific set of conditions in the stellar interior, and they contribute disproportionately to the cosmic carbon budget. They're the primary source of carbon dust in the universe, the soot that eventually becomes graphite in meteorites, the carbon that becomes part of organic molecules. Life, which is based on carbon, owes a debt to carbon stars. Let this image settle in your mind. Carbon stars, glowing red and infrared, dominating the long wavelength sky. You don't need to see them. You don't need to understand the chemistry of carbon-rich atmospheres. Just let them be there, glowing quietly in the darkness. Ancient, patient, near the end, and let yourself glow too, if you want. Not visibly, not brightly, but in the infrared, in the long wavelengths of rest, in the deep, invisible warmth of sleep. The carbon stars glow redder. The infrared sky is dominated by their emission. The dust clouds radiate, and you are allowed to radiate too, in the invisible spectrum of rest, in the long, slow wavelengths of unconsciousness. Let the carbon stars glow. Let the infrared dominate. And let yourself become a source of invisible warmth, glowing gently in the darkness of sleep. Interstellar impact. Red giant winds deposit vast amounts of dust galaxy-wide. And now we reach the final fact, the culmination, the big picture. Red giant winds, collectively, across the entire galaxy, deposit vast amounts of dust into the interstellar medium. Millions of red giants, each one losing mass, each one forming dust, each one enriching space with heavy elements and solid particles. The impact is enormous. Estimates suggest that red giants and their descendants, asymptotic giant branch stars, planetary nebulae, contribute the majority of the dust in the interstellar medium, more than supernovae, more than any other source. This dust has consequences. It affects star formation. It affects the chemistry of molecular clouds. It affects the evolution of galaxies. Without dust, the universe would be a very different place. Stars would form more slowly. Planets would be harder to make. Life might not arise at all. The dust from red giant winds is, quite literally, the foundation of cosmic complexity. And this dust is everywhere, in every galaxy, in every star-forming region, drifting between the stars, absorbing starlight, re-radiating it in the infrared, shaping the thermal balance of the interstellar medium. It's invisible mostly. You can't see it with the naked eye, but it's there. A vast, diffuse ocean of tiny grains, spread throughout the galaxy, the product of billions of years of red giant evolution. There is something almost overwhelming about this scale. The vastness of the impact, the importance of these aging stars, the way their final act of shedding mass becomes a foundation for future generations. But don't be overwhelmed. Just let the scale wash over you. Let it remind you of how interconnected everything is. How small acts, repeated many times, can have galaxy-wide consequences. Your own small acts matter too. Your thoughts, your choices, your rest. Rest is not selfish. It's necessary. It's the foundation for tomorrow's wakefulness. Just as the dust from red giants is the foundation for tomorrow's stars. So let yourself rest. Let yourself deposit galaxy-wide the peace that comes from letting go. The red giants deposit dust. The impact is vast. The galaxy is enriched. And You have reached the end of this journey. 60 facts about red giants, from their formation to their final winds, from their cores to their dust. And now you can rest. Let the facts fade. Let the numbers blur. Let the images dissolve. You have drifted through the realm of red giants. You have explored their interiors, their atmospheres, their winds, their dust. And now you can let it all go. The red giants continue. They will shine long after this night has passed. They will pulse and vary and shed their masks, patient and ancient, lighting the darkness. And you are allowed to simply sleep. The interstellar impact is vast. The dust is deposited. The galaxy is transformed. And you are transformed too. From waking to sleeping. From thought to stillness. From complexity to the simple, profound peace of rest. Let the red giants glow in the distance. Let their winds blow through the cosmos. And let yourself drift finally, completely, into the warm, dark, infinite embrace of sleep. Good night, sleepy soul. Rest well among the stars. The facts are complete. The journey is done. There is nothing more you need to know tonight. The red giants will continue to glow. The universe will continue to unfold. And you are allowed to simply rest. Let sleep find you. Let it hold you. Let it carry you through the hours of darkness until the morning comes and you wake renewed. But for now, just rest. Just breathe. Just let go. The cosmos is vast. You are small, and that is beautiful. Sleep well.